Imagine a cosmic lighthouse so powerful, it can outshine an entire galaxy, not just for a moment, not for a flash, but for millions, even billions of years. And now, imagine that same lighthouse doesn't just shine from a single point, but unleashes twin beams of energy across the universe, spanning hundreds of thousands of light years in opposite directions. What are these mysterious double-headed monsters lurking in the far reaches of space? What kind of unimaginable forces could sculpt something so massive, so violent, and yet so symmetrical? These are no ordinary quasars. These are double-lobed quasars, cosmic engines so strange, so misunderstood, that even the most seasoned astrophysicists remain baffled by their structure, formation, and behavior. But before we continue, subscribe to the channel so you don't miss any of these videos. This isn't just another science video. This is a deep dive into the heart of the universe's most powerful phenomena. We're going to journey through space and time, peel apart the layers of radiation, gravity, and matter, and trace the fingerprint of the unimaginable forces that birth these colossal double-lobed entities. And by the time we emerge, you won't just know what a double-lobed quasar is, you'll understand why it might just be one of the keys to unlocking the biggest questions in the cosmos. To fully grasp what a double-lobed quasar is, we need to take a long step back, far away from Earth, beyond our solar system, past the serene swirls of the Milky Way, and deep into the chaotic, energetic cores of distant galaxies. In the hearts of these galaxies lie supermassive black holes, some with masses equivalent to billions of suns. These black holes don't just sit there consuming matter silently. Under the right conditions, they become the centers of unimaginably powerful activity. They devour gas, dust, and sometimes even stars, and as they do, they ignite a process so ferocious that it lights up the entire galaxy. This process gives birth to what we call quasars. Quasars, or quasi-stellar objects, are incredibly bright and distant objects powered by the accretion of material into supermassive black holes. From Earth, they often appear like stars in early telescopes, hence the name, quasi-stellar. But behind that stellar disguise is an inferno of physics unlike anything else in the known universe. As material spirals into a black hole's accretion disk, it heats up to millions of degrees, producing enormous amounts of radiation, often outshining the entire galaxy that hosts it. But here's where things get even stranger. Some quasars aren't content to shine from a single point. In rare cases, they eject matter in opposite directions along their rotational axis, forming colossal lobes of radio-emitting plasma. These lobes can stretch out for hundreds of thousands, even millions of light years, far beyond the confines of the galaxy that spawned them. That's when a quasar becomes a double-lobed quasar. And suddenly, the mystery deepens. A double-lobed quasar isn't just an energetic black hole, it's a cosmic firehose, spraying jets of ionized material into intergalactic space with such speed and precision that the resulting structure resembles two colossal wings extending out from a galactic core. These structures can often be seen in radio frequencies rather than visible light, and they are among the most awe-inspiring phenomena in the universe. The reason these lobes form is due to the relativistic jets, beams of charged particles accelerated to nearly the speed of light, that are produced by the intense magnetic fields near the black hole's poles. These jets, when powerful enough, can punch through the surrounding medium and continue traveling through intergalactic space. As they do, they plow into the thin gas between galaxies, heating it up and creating radio-bright lobes. These jets don't just leave a trail, they leave vast, glowing footprints. But it's not as simple as turning on a jet engine and watching it fire. The formation of these jets, and their transformation into massive lobes, is governed by incredibly complex interactions of magnetohydrodynamics, relativity, gravity, and quantum mechanics. And to make things even more intriguing, only a small fraction of quasars become double-lobed. Why some do and others don't is still one of astronomy's enduring questions. Are double-lobed quasars the result of specific galactic environments? Do they depend on the spin of the black hole? Is it a matter of alignment, or are we only seeing a select few because of our viewing angle from Earth? These are questions researchers are still trying to answer, and every discovery opens up even deeper mysteries. When observed, double-lobed quasars reveal perfect symmetry. but the universe is anything but perfect. How do such symmetrical structures emerge from a chaotic, turbulent environment like a galactic center? The answer lies, at least in part, in the alignment of the black hole's spin axis and the configuration of the surrounding magnetic fields. When the spinning black hole and its magnetic field align just right, they can create a stable, focused beam of particles shooting in both directions. These jets eventually slow down and inflate into the radio lobes we see, far beyond the edges of the galaxy. The lobes themselves are filled with plasma, highly energetic particles moving at near light speed. They emit synchrotron radiation, a type of electromagnetic radiation generated when charged particles spiral through magnetic fields. This radiation is brightest in the radio part of the spectrum, which is why most double-lobed quasars are first discovered by radio telescopes. Interestingly, these lobes don't last forever. Over millions of years, they fade, losing energy and blending back into the intergalactic medium. Yet even in their decay, they leave behind relics, giant ghostly shadows in radio space. Some researchers speculate that relic lobes could provide critical clues about the universe's expansion, the structure of dark matter, and the history of galactic evolution. One of the most iconic examples of a double-lobed quasar is 3C273. Although it is not the most distant or the most massive, it is one of the first quasars ever discovered, and it gave scientists their first real glimpse into the true power of these cosmic engines. Observing quasars like 3C273 helped astronomers realize that these were not stars, but something far more powerful and distant, lying billions of light years away and offering glimpses into the early universe. Double-lobed quasars are more than just scientific curiosities. They're beacons, illuminating the paths of jets that travel through space-time itself. Their orientation, shape, size, and radiation tell us about the history of the galaxy that birthed them, the black hole that powers them, and even the nature of the intergalactic space they move through. They also serve as cosmic laboratories for testing the extremes of physics, from general relativity to quantum electrodynamics. Studying these giants can help refine our models of how galaxies form and evolve. They might even help us detect gravitational waves or understand the role of magnetic fields in cosmic structures. Some researchers believe that double-lobed quasars could also help trace the formation of the cosmic web, the vast, filamentary network of galaxies and dark matter that makes up the large-scale structure of the universe. And as we build better telescopes, like the Square Kilometre Array and the next generation of space observatories, we'll be able to observe these lobes in greater detail than ever before. This might finally answer some of the fundamental questions. How do the jets form? How do they stay so focused across such vast distances? What determines their shape, symmetry, and energy output? And most importantly, what are they trying to tell us about the universe? Every time we discover a new double-lobed quasar, it's like unearthing a fossil from the deep past of the cosmos. These structures are time capsules, preserving the violent, beautiful history of galaxies and black holes. And perhaps, just perhaps, they hold the secrets to understanding our own origins in this ever-expanding universe. When gas, dust, and even entire stars are drawn into the gravitational pull of these supermassive black holes, they don't fall in directly. Instead, they spiral inward, forming a disk of incredibly hot material called an accretion disk. This disk spins faster and faster, compressing matter under immense pressure and generating radiation on a colossal scale, so immense, in fact, that it can outshine the combined light of billions of stars in the host galaxy. This is what astronomers refer to as a quasar, short for quasi-stellar radio source. Because when first discovered, these intense points of light appeared star-like, yet emitted unusual and powerful radio waves. But while many quasars appear as a single brilliant point, there is a rarer, far more enigmatic variant, the double-lobed quasar. Unlike their compact counterparts, these quasars display a structure that extends far beyond their central cores, two massive lobes of radio-emitting plasma, stretching out in opposite directions, sometimes spanning distances longer than the entire diameter of the Milky Way. These lobes aren't just decorative wings, they are the signature of immense jets, streaming out from the poles of the quasar at nearly the speed of light. And they raise one of the most profound mysteries in astrophysics. How can something so symmetrical, so vast, and so persistently stable be forged in the midst of such chaos? The creation of these double-lobed structures begins with the black hole's magnetic field. When the material in the accretion disk becomes turbulent and electrically charged, it generates powerful magnetic fields that thread through the spinning disk. These magnetic fields can twist and funnel material along the axis of rotation of the black hole, accelerating it outward in the form of jets. What's extraordinary is that these jets don't just shoot out for a moment and fade, they persist, sometimes for millions of years, drilling through the galactic medium and inflating gigantic bubbles of radio-emitting plasma on either side of the galaxy. These bubbles, what we see as lobes, are filled with relativistic particles spiraling through magnetic fields, emitting radiation through a process called synchrotron emission. The result is a pair of glowing lobes that shine in radio wavelengths, symmetrically placed across the galactic core. And here's where things get even stranger. Not all quasars produce these jets, and not all jets produce lobes. The conditions needed to sustain a double-lobed quasar are incredibly specific, and even now, astrophysicists are working to decode why only certain galaxies, and only certain supermassive black holes, give rise to these awe-inspiring structures. Part of the mystery lies in the orientation. If a jet is pointed directly toward us, the quasar appears as a different type of object altogether, a blazar. But when viewed from the side, we can see the full extent of the lobes. This viewing angle, combined with the presence of a dense intergalactic medium and a stable central engine, contributes to the emergence of these elegant lobe forms. Some lobes are so extended that they remain visible long after the central quasar has gone quiet, leaving behind relics of ancient energy ejections like cosmic footprints etched across the void. And this isn't just a question of beauty or symmetry. Double-lobed quasars are messengers from the deep past. Because they are so distant, the light and radio waves we observe from them were emitted billions of years ago. Every double-lobed quasar is a time capsule, telling us not only about the conditions of its own host galaxy, but also about the nature of the early universe. The energy from these jets can shape entire galaxies, heating intergalactic gas, suppressing or triggering star formation, and redistributing matter on colossal scales. More than that, these structures could help us refine our understanding of fundamental physics. The behavior of matter at relativistic speeds, the dynamics of magnetic fields in extreme conditions, and the role of black holes in galaxy formation, all of it is embedded in the study of these giant lobes. Some researchers believe that by analyzing their spectra, polarization, and evolution over time, we might even uncover clues about dark matter, dark energy, or deviations from the standard model of cosmology. There are also anomalies, objects that appear to be double-lobed quasars but don't quite fit the mold. Some display lobes that are asymmetrical, others seem to have restarted their jets multiple times, producing nested pairs of lobes like Russian dolls of plasma. These are known as double-double radio galaxies, and they raise questions about how stable and continuous the activity of a black hole can be. Are these black holes flickering on and off over cosmic timescales? Are they being fed by waves of infalling matter, each one reigniting the jets? Then there's the question of scale. The largest double-lobed structures, known as giant radio galaxies, can stretch over several megaparsecs, millions of light years. These are among the largest single objects in the universe, and their discovery has pushed the limits of what we thought was possible for galactic structures. How do jets maintain their coherence over such vast distances? What prevents them from dispersing or being deflected by the intergalactic medium? The answers may lie in simulations, using supercomputers to model the behavior of plasma jets, magnetic fields, and gravitational forces at scales that no laboratory on Earth could hope to reproduce. But even our best models struggle to account for all the variables. The interplay between the black hole's spin, the rate of accretion, the structure of the host galaxy, and the properties of the surrounding medium all influence whether a double-lobed quasar will form, and how long it will last. Astronomers also use very long baseline interferometry, VLBI, to resolve the fine details of these objects. This technique combines data from radio telescopes spread across the planet, essentially turning the Earth itself into a giant lens. Through VLBI, we can peer into the very heart of active galactic nuclei, tracing the formation of jets with exquisite precision. These observations have revealed shock fronts, knots of energy, and corkscrew patterns in the jets that may correspond to precession, the slow wobble of the black hole's axis, or interactions with surrounding matter. As we push deeper into the data, new mysteries emerge. Some double-lobed quasars seem to be spinning in opposite directions, with jets that curve away from each other rather than pointing straight. This could indicate that the black hole has merged with another, or that powerful gravitational forces are at play, distorting the symmetry. In other cases, the lobes appear displaced, suggesting that the entire galaxy may have shifted between outbursts, perhaps due to galactic collisions or other dramatic events. Even more intriguing are the so-called X-shaped or winged radio galaxies. In these objects, the lobes form a distinct cross shape, with secondary lobes branching off at right angles from the primary jets. What causes this bizarre morphology? Some theories suggest that the central black hole may have suddenly reoriented, perhaps after a merger with another supermassive black hole, sending jets in a new direction, while the old lobes faded into ghostly wings. These are not mere curiosities. Each variation tells a story, a cosmic drama playing out over eons, involving gravity, magnetism, and matter pushed to their absolute extremes. And because these objects are so far away, we're not just looking at distant places, we're looking at ancient times. Some of the double-lobed quasars we observe today were active when the Earth was still forming, when the first molecules of life had yet to emerge. These magnetic fields can twist and channel enormous amounts of energy into narrow, focused beams that shoot out along the rotational axis of the black hole. These beams, known as relativistic jets, consist primarily of charged particles, electrons and positrons, that have been accelerated to nearly the speed of light. As these jets extend into the vastness of space, they eventually collide with the intergalactic medium, which is the sparse collection of gas and plasma that exists between galaxies. This collision is not gentle. The jets plow into the surrounding medium, compressing it and heating it to extreme temperatures. As the particles slow down and disperse, they form enormous, balloon-like structures at the far ends of the jets. These structures are the lobes, the iconic double-lobed feature that gives these quasars their name. Each lobe is a colossal repository of energy, emitting strongly in the radio spectrum due to synchrotron radiation. This occurs when the high-speed electrons spiral around magnetic field lines, releasing their energy in the form of radio waves. What's truly astonishing is the scale. These lobes can span anywhere from tens of thousands to millions of light-years across. To put that in perspective, the entire Milky Way galaxy is about 100,000 light-years wide. These lobes can easily dwarf it in size. And yet, despite their staggering proportions, they remain aligned, symmetrical, and balanced, suggesting that the mechanisms fueling their formation are both stable and finely tuned over immense timescales. But double-lobed quasars aren't just visually striking, they're also cosmological time capsules. The light and radio emissions we detect from them have taken millions, sometimes billions of years to reach us. That means when we observe one, we're not seeing it as it is today. We're looking back in time, witnessing events that occurred when the universe was younger, denser, and more volatile. This makes double-lobed quasars invaluable to astronomers trying to understand the evolution of galaxies and the behavior of supermassive black holes during the early epochs of cosmic history. To detect and study these distant objects, astronomers rely heavily on radio telescopes. Optical telescopes often fall short because the core of a quasar can be so bright that it overwhelms surrounding features, or because the light is redshifted far out of the visible spectrum due to the expansion of the universe. Radio waves, however, penetrate the dust and gas that might obscure visible light and provide a clearer picture of the extended structures, the jets and the lobes. Using radio interferometry, which combines data from multiple telescopes spread across large distances, scientists can construct incredibly detailed images of these distant phenomena. One of the most compelling aspects of double-lobed quasars is their role in shaping galactic environments. The jets and lobes don't simply drift passively through space. They exert pressure on their surroundings, heating up gas, triggering or halting star formation, and influencing the growth of the host galaxy. This interaction is a form of feedback, a regulatory process that can either nurture or suppress further galactic development. In some models of galaxy formation, such feedback mechanisms are essential to explaining why galaxies have the sizes, masses, and compositions they do today. The symmetrical appearance of the lobes is a fascinating puzzle. It implies a long-term consistency in the orientation and intensity of the jets being produced. This is surprising because the central regions of galaxies are anything but calm. Collisions, mergers, and inflows of gas should, in theory, disrupt the black hole's accretion disk and the orientation of the jets. And yet, many double-lobed quasars show signs of persistent structure, suggesting either that the forces stabilizing the system are incredibly robust, or that we are only seeing a narrow window of time when such symmetry happens to exist. Another mystery lies in the triggering mechanism. Not all quasars produce lobes. Some are compact, lacking the massive twin structures that define the double-lobed variety. Why do some black holes generate these powerful jets while others do not? Is it a matter of spin? Perhaps only rapidly rotating black holes can twist magnetic fields strongly enough to launch jets? Or is it about the surrounding environment? Maybe only certain types of galaxies provide the right conditions for jets to grow and lobes to form? Recent simulations suggest that spin may indeed play a key role. A spinning black hole drags spacetime around with it, a phenomenon known as frame dragging. This twisting of space itself could help collimate the magnetic fields and focus the jets. But other models emphasize the role of magnetic flux, the idea that the strength and configuration of magnetic fields around the accretion disk determine whether a jet forms and how powerful it becomes. There's also the possibility that both spin and magnetic flux are necessary conditions, working in tandem to create the perfect storm that births a double-lobed quasar. Observational data further complicates the picture. Some double-lobed quasars display symmetries. One lobe may appear brighter, closer, or more developed than the other. This could be due to Doppler boosting, where the jet moving toward us appears more intense due to its motion, while the receding jet seems dimmer. Alternatively, it could be the result of differences in the intergalactic medium. Perhaps one side of the galaxy lies in a denser region of space, causing the jet to decelerate and dissipate more rapidly. Each scenario provides clues, but also raises new questions. Another key feature often associated with double-lobed quasars is the so-called hot spots at the ends of the lobes. These are regions of intense emission where the jet's energy is most concentrated. They mark the points where the jets crash most violently into the intergalactic medium. From these hot spots, the energy flows backward toward the core, forming the broader lobe structure. Understanding the dynamics of these regions, how particles are accelerated, how magnetic fields behave, how energy is transferred, can offer insight not just into quasars, but into fundamental plasma physics under extreme conditions. We're seeing it as it was millions or even billions of years ago, a snapshot frozen in deep cosmic time. Each double-lobed quasar, then, is a message from the distant past, offering clues about the early universe, the growth of galaxies, and the behavior of supermassive black holes in their most active stages. The jets and lobes act like cosmic footprints, preserving a record of the quasar's energy output, direction of spin, and even changes in its activity level over epochs. One particularly intriguing detail is how these lobes remain visible long after the central quasar becomes dormant. After the black hole has consumed most of the matter available to it, and the accretion disk fades, the jets eventually shut down. However, the lobes can linger for hundreds of millions of years, glowing faintly in radio wavelengths like ghostly remnants of a once dominant galactic engine. These so-called relic lobes are key to understanding the life cycle of active galactic nuclei and how their influence stretches far beyond their active lifetimes. The orientation of the jets, and therefore the lobes, also tells scientists about the alignment and spin of the central black hole. If the black hole is tilted relative to its host galaxy, or if it's part of a galaxy merger, the direction of the jets may shift over time. Some double-lobed quasars even show signs of jet precession, where the lobes appear to curve, twist, or fork, suggesting that the black hole's axis has changed direction slowly, like a spinning top wobbling as it slows. This precession may be caused by gravitational interactions with nearby black holes or by shifts in the angular momentum of infalling material. Double-lobed quasars aren't merely artistic curiosities. They are forceful agents of galactic transformation. Their jets and lobes carry energy and momentum far beyond their galaxies, heating intergalactic gas, quenching star formation by blowing away gas that would otherwise condense into new stars, or in some cases triggering new waves of star birth by compressing clouds of matter on the galactic outskirts. This means they play a major role in galaxy evolution, shaping the fates of their surroundings for eons. Astronomers study double-lobed quasars using powerful radio telescopes like the Very Large Array, VLA, in New Mexico, or the Low Frequency Array, LOFAR, in Europe. These instruments allow researchers to map the extent and structure of the lobes in astonishing detail, revealing knots, filaments, hotspots, and shock fronts that trace the journey of particles over cosmic distances. In some cases, a single quasar's jets can be traced across nearly the entire diameter of the sky if they're relatively close to us. But what makes a quasar double-lobed instead of compact or featureless? One major factor is the environment it resides in. Galaxies rich in interstellar and intergalactic gas provide the necessary resistance for the jets to interact, decelerate, and puff into visible lobes. In sparser environments, the jets may continue unimpeded and fade without leaving behind large radio structures. The strength of the magnetic fields, the spin rate of the black hole, the rate of accretion, and the age of the system all combine in complex ways to determine the final appearance. There is also a class of objects closely related to double-lobed quasars, radio galaxies. These are also powered by supermassive black holes and produce giant jets and lobes. But unlike quasars, their central cores are less optically luminous, often because the accretion disk is either faint or obscured by dust. The distinction between radio galaxies and double-lobed quasars can sometimes blur, as both represent stages or variations in a broader family of active galactic nuclei, AGN. In fact, many researchers now see them as part of a spectrum, unified by the same physical mechanisms but appearing different based on viewing angle and stage of evolution. There are also unusual subtypes that challenge classification altogether. Some double-lobed quasars display X-shaped lobes, possibly indicating a past jet reorientation, perhaps due to a black hole merger. Others are misaligned, bent, or show triple lobes, suggesting complex histories of interaction and evolution. These atypical structures defy simplistic explanations and require advanced modeling, often involving simulations that span millions of years and thousands of light-years in virtual space. The more we study these cosmic behemoths, the more we realize they are not just passive consequences of black hole activity. They are engines of change, writing their influence into the architecture of the universe itself. They regulate the formation of stars, the growth of galaxies, and even the structure of the cosmic web. Double-lobed quasars may seem rare, but their impact is outsized. And they hold the key to questions as profound as, how do galaxies grow? How do black holes shape the universe? What governs the flow of energy across cosmic scales? In other cases, the intense heat and pressure from these jets can do the opposite, disperse gas clouds and suppress star formation by heating the interstellar and intergalactic medium. This phenomenon, known as AGN feedback, is a crucial concept in modern astrophysics. Active galactic nuclei, particularly those in double-lobed quasars, can regulate the growth of their host galaxies by controlling how much cold gas is available for new stars to form. If too much gas gets swept away or heated beyond the point where it can condense, entire galaxies may stop forming stars altogether, effectively ending their period of stellar birth. This regulation mechanism helps explain one of the long-standing puzzles in cosmology: why massive galaxies tend to be red and dead, meaning they're composed mostly of older, red stars and show little to no signs of ongoing star formation. Without the influence of AGN feedback, simulations of the universe's evolution tend to produce galaxies that are too massive and too full of young, blue stars. But when the powerful effects of quasar jets and lobes are factored in, especially those of the double-lobed variety, these simulations begin to align much more closely with what astronomers actually observe. And yet, despite all we've learned, the exact physics behind the launching and collimation of these jets remains one of the great open questions in astrophysics. How do magnetic fields, plasma dynamics, and relativistic effects combine to produce such narrow, coherent beams that can remain stable over millions of light years? Why do some quasars develop these vast lobes while others do not? Is it simply a matter of orientation, meaning we're only able to detect the lobes in certain cases? Or is there a deeper difference in the internal workings of these black holes? Some theories suggest that the spin of the black hole itself plays a pivotal role. In a mechanism known as the Blandford's-Nagic process, it's proposed that energy can be extracted from a rotating black hole if it's threaded by magnetic field lines. These lines twist and wind through the ergosphere, the region just outside the event horizon, drawing out rotational energy and launching it into space as powerful jets. The faster the spin, the more energy can be extracted, and the more formidable the resulting jets. This also raises a tantalizing implication. Double-lobed quasars might be a sign of rapidly spinning supermassive black holes. If we can better understand the conditions under which these lobes form, we could gain insights into how black holes grow, merge, and evolve over cosmic time. Observing the jets may even allow us to probe regions of spacetime near the event horizon, areas that are otherwise completely inaccessible to direct observation. But the story of double-lobed quasars doesn't just unfold in deep space, it unfolds across time. Some of the most ancient quasars we've ever observed, formed less than 1 billion years after the Big Bang, already show signs of lobe formation. That means these cosmic structures were not only present but also fully functional in the very early universe. They may have played a vital role in the formation of large-scale cosmic structures, shaping the filamentary web of galaxies, clusters, and voids that stretch across the universe today. The role of double-lobed quasars in the early universe is fascinating because they offer one of the clearest windows into the mechanisms that shape the large-scale structure of the cosmos. The jets launched by these active galactic nuclei didn't just spew energy and matter outward. They also influenced the way galaxies grouped together, spread out, and interacted. The intergalactic medium, the vast region of space between galaxies, was significantly affected by the energy released from quasars. The intense radiation and material expelled by these supermassive black holes could heat up the surrounding gas, preventing it from collapsing into new stars, or alternatively, compress it, sparking the formation of new stellar clusters. This process could have helped regulate how the universe transitioned from an early, chaotic, and dense state to a more structured, modern cosmos. In essence, these double-lobed quasars were not just creating star systems, but were also actively shaping the very environment in which galaxies could evolve. The high-speed particles and shockwaves emanating from these objects acted like a cosmic pruning mechanism, which helped to define the balance between the creation and destruction of matter in the early universe. We're now at a point in astrophysical research where we have an unprecedented understanding of these far-flung phenomena. Thanks to observational technology like the Hubble Space Telescope, the Chandra X-ray Observatory, and radio telescopes like the Very Large Array, VLA, and LOFAR, we're now able to observe these quasars in much finer detail than ever before. But we still have a long way to go before we can fully unlock all their secrets. For example, despite the wealth of data we've gathered, scientists are still piecing together the relationship between the jet material and the material in the accretion disk of the black hole. The question remains, how are the powerful jets launched in the first place? What is the exact mechanism behind their collimation, the narrowing of the jets into narrow beams? And why do some quasars have these highly structured lobes while others don't? These are some of the many questions that keep astronomers up at night. One idea that's being explored more actively in recent years is the role of galaxy mergers. We know that when galaxies collide, they can dramatically alter the behavior of their central black holes, and possibly their accretion disks as well. Could some of these double-lobed quasars be the result of black holes undergoing a merger, with the interaction between the two triggering new activity in the form of jet emissions? This hypothesis could provide new insights into the evolution of galaxies and their supermassive black holes. Merging galaxies are known to result in a powerful release of energy, often in the form of gravitational waves, a phenomenon first detected by the LIGO collaboration. When two supermassive black holes merge, it's believed that the immense gravitational forces at play could cause the system to release energy in the form of both gravitational waves and highly energetic jets. It's possible that the phenomenon we observe as double-lobed quasars is related to these galaxy mergers, which might have been common in the universe's early years, when galaxies were still colliding and combining at a much higher rate. The next piece of the puzzle is the study of feedback loops in the evolution of supermassive black holes. As mentioned earlier, quasars are known to play a major role in the life cycles of galaxies. But the energy output from a quasar's jets doesn't just influence the galaxy where it resides. Instead, it affects the surrounding intergalactic medium. The energy pushed out by the lobes can be so immense that it prevents nearby gas clouds from collapsing into new stars, ultimately slowing or halting star formation in the host galaxy. This means that these powerful objects also regulate their own growth. Once the black hole has consumed most of the matter around it, its accretion disk weakens, and its jets may become less powerful, or even cease entirely. But because the black hole has already released so much energy, this reduction in activity doesn't necessarily result in the galaxy returning to a state of unchecked star formation. Instead, the environment around the galaxy has already been altered in a way that prevents new stars from being born. This intricate process is referred to as AGN feedback, and it plays a major role in determining the overall evolutionary path of a galaxy. The understanding of double-lobed quasars also leads us to broader questions about the structure of the universe. These quasars are not just isolated objects in deep space. They are also part of a grander narrative about the evolution of large-scale structures in the cosmos. The jets and lobes produced by these quasars often stretch across vast distances, sometimes hundreds of thousands, or even millions of light years. The materials in these lobes are not simply ejected into empty space. They interact with the intergalactic medium, the gas, that fills the voids between galaxies. This interaction can lead to phenomena like shock waves that spread across great distances, helping to mold the cosmic structures we see today. As these shock waves propagate, they can induce a variety of fascinating astrophysical phenomena. For instance, when these waves collide with gas clouds, they can compress the gas, potentially triggering the formation of new stars. On the other hand, when they pass through already formed star systems, they can disrupt stellar orbits, and even strip away material from those stars. This interplay between quasars and the surrounding environment suggests that double-lobed quasars are not just powerful beacons of light but also central to the dynamic processes that drive the evolution of galaxies and their intergalactic environments. Moreover, the impact of double-lobed quasars extends beyond the confines of individual galaxies. The vast lobes and jets emitted by these objects influence the way galaxies group together in cosmic clusters. The jets can create vast cavities of low-density gas in these clusters, affecting the overall distribution of matter in these regions. These cavities are often referred to as radio bubbles, or radio lobes, and can stretch across millions of light years. Over time, these bubbles can cause significant disruption in the hot gas that permeates galaxy clusters, which plays a crucial role in the way clusters evolve. In this sense, the jets from double-lobed quasars are not just shaping their immediate environments, they're also having a profound impact on the largest structures in the universe. While these processes have been theorized for years, recent advancements in observational technology have allowed us to observe these interactions in greater detail. With instruments like the Atacama Large Millimeter/Submillimeter Array (ALMA) and Very Large Telescope (VLT), astronomers can study the gas surrounding quasars with unprecedented precision. This has led to new insights into the way quasars interact with their environment, particularly when it comes to the formation of galaxy clusters. In the future, as our observational capabilities continue to improve, we may be able to uncover even more about the role of double-lobed quasars in the development of large-scale cosmic structures. The jets emitted by these quasars are also a valuable tool for studying some of the most extreme and fundamental aspects of physics. The high speeds at which the jets travel, often approaching a significant fraction of the speed of light, allows scientists to probe the properties of relativistic particles. These particles are not only moving incredibly fast but also interacting in ways that provide insights into general relativity and quantum mechanics. As the jets propagate outward, they often collide with other cosmic objects, creating shock waves and high-energy phenomena that can be studied to learn more about the behavior of matter and energy under extreme conditions. These observations allow us to test some of the most exotic predictions of modern physics. For example, one of the most exciting prospects of studying double-lobed quasars is the potential to observe gravitational lensing. When light from a distant quasar passes near a massive object, such as another galaxy or even a cluster of galaxies, the gravitational pull of that object can bend the light, causing the quasar to appear multiple times or in distorted shapes. This phenomenon provides a natural laboratory for testing our understanding of how gravity works on a cosmic scale. Gravitational lensing also allows us to study the distribution of dark matter, which, although invisible, has a significant influence on the way light bends around massive objects. At the heart of these quasars lies the supermassive black hole, the engine that powers the entire system. These black holes are not just passive objects, they are active participants in the cosmic drama unfolding in and around them. The immense gravitational forces around them cause matter to spiral inward, forming the accretion disk, which in turn generates the powerful radiation and jets that define quasars. The question of how these supermassive black holes form and grow is one of the biggest mysteries in modern astrophysics. Do they start off as smaller black holes that gradually merge over time, or do they form in a more exotic manner, perhaps as a result of the collapse of massive gas clouds in the early universe? The answer to this question has important implications for our understanding of galaxy evolution. Supermassive black holes and the quasars they power are thought to have a profound influence on their host galaxies. As these black holes grow, they can alter the structure of their host galaxies in subtle yet profound ways. For example, as quasars release vast amounts of energy, they can blow away surrounding gas and dust, preventing the formation of new stars. This feedback mechanism is believed to play a crucial role in regulating the size and star formation rates of galaxies, helping to explain why some galaxies are quenched and cease forming stars. Double-lobed quasars, with their powerful jets, are perhaps the most extreme examples of this feedback process. By pushing out vast amounts of energy and material, these quasars can not only disrupt their own galaxies but also influence neighboring galaxies and the larger cosmic web. The jets from a quasar in a galaxy cluster can even extend far enough to affect the intracluster medium, potentially preventing the formation of new stars across vast regions of space. This feedback mechanism is crucial for understanding how galaxies evolve and why some galaxies become red and dead, with no new stars being born. Understanding double-lobed quasars is also essential for understanding the evolution of supermassive black holes themselves. These objects are some of the most mysterious and enigmatic entities in the universe. Despite their name, black holes are not black, in the traditional sense. They emit radiation and have a profound effect on their surroundings. As we learn more about the powerful jets emitted by these black holes, we gain deeper insights into the physics of black holes and the role they play in shaping the universe. In particular, the relationship between the black hole's spin, its accretion disk, and the jets it produces is a key area of research. By studying this relationship, we hope to unlock some of the most profound mysteries of modern physics, including the nature of space, time, and gravity. As we continue our exploration of double-lobed quasars, it's important to dive deeper into the connection between these objects and the broader evolution of the universe. Understanding quasars isn't just about observing individual objects, but about piecing together a larger narrative of cosmic evolution. The insights we gain from studying these powerful phenomena help scientists to fill in the gaps in our knowledge about the formation and growth of galaxies, the behavior of matter under extreme conditions, and the intricate dynamics of the universe as a whole. One particularly intriguing aspect of studying double-lobed quasars is their connection to the growth of galaxies. As the jets emitted by quasars interact with their environments, they shape the structure of the host galaxy in ways that are still being unraveled. These interactions are not just isolated events, they have long-term consequences for the life cycle of galaxies. The energy and matter ejected from the black hole's jets can heat the surrounding gas to the point where it prevents further star formation, essentially quenching the galaxy. This process of feedback is thought to be one of the key mechanisms in galaxy evolution, and quasars, with their immense energy output, are believed to play a significant role in this cosmic regulation. But the influence of double-lobed quasars isn't limited to the galaxies in which they reside. The jets from these supermassive black holes can extend far beyond their host galaxies, often stretching across hundreds of thousands, or even millions of light years. These jets and their associated lobes can have a profound impact on the intergalactic medium, the vast and largely invisible expanse of gas that exists between galaxies. When a quasar's jets collide with the gas in the intergalactic medium, they can create massive shock waves, which in turn can compress gas clouds and trigger the formation of new stars. These shocks can also create bubbles of low-density gas, known as radio bubbles, which can distort the surrounding cosmic structures. These large-scale interactions illustrate just how interconnected the universe is on the grandest of scales. The impact of a double-lobed quasar's jets can ripple through the fabric of the cosmos, influencing the distribution of matter, the rate of star formation, and even the structure of galaxy clusters. As astronomers continue to study these effects, they are uncovering new insights into how galaxies grow, evolve, and interact over vast stretches of cosmic time. Moreover, the study of these jets is revealing new information about the behavior of relativistic particles and magnetic fields. The jets emitted by double-lobed quasars are often made up of charged particles moving at speeds that approach the speed of light. As these particles travel through the magnetic fields of the host galaxy and the intergalactic medium, they generate powerful electromagnetic radiation, which can be detected across vast distances. By studying this radiation, astronomers can learn about the properties of the magnetic fields that shape the jets, as well as the fundamental physics that governs the motion of these relativistic particles. This ability to study the behavior of high-energy particles and magnetic fields is one of the key reasons why quasars and their jets are such valuable tools for understanding fundamental physics. The extreme conditions near a supermassive black hole provide a natural laboratory for testing our understanding of general relativity, quantum mechanics, and the behavior of matter and energy in extreme environments. The radiation emitted by these jets can also provide valuable clues about the structure of space-time itself, potentially offering insights into the nature of dark matter, dark energy, and even the origins of the universe. One of the most exciting prospects in the study of double-lobed quasars is the possibility of using them to explore the properties of exotic matter. This is the hypothetical form of matter that behaves in ways that are entirely different from anything we are familiar with, such as particles with negative mass or the ability to travel faster than light. While such matter remains purely theoretical, quasars, especially those with powerful, relativistic jets, could provide the best opportunity to detect signs of this exotic matter. If we can observe the behavior of particles and energy in these extreme environments, we may one day be able to unlock the mysteries of some of the most fundamental questions in physics. Moreover, quasars provide a unique opportunity to explore the large-scale structure of the universe. The jets emitted by double-lobed quasars often extend across vast stretches of space, interacting with the gas and matter between galaxies. These interactions provide important clues about how galaxies cluster together, how they evolve over time, and how they are affected by the cosmic web, the vast network of filaments, voids, and clusters that make up the large-scale structure of the universe. By studying quasars, we can gain insights into the forces that shape the universe on the grandest scales, helping us to understand the origins and future of the cosmos itself. Another aspect of double-lobed quasars that is gaining increasing attention is their connection to the early universe. Most of the quasars we observe today are located at vast distances, meaning that the light we are seeing has traveled for billions of years before reaching us. This means that we are essentially observing these quasars as they were in the distant past, when the universe was much younger. By studying the properties of these distant quasars, scientists can learn about the conditions in the early universe and how galaxies and black holes evolved over time. For example, some of the most distant quasars we have observed appear to be powered by supermassive black holes that formed just a few 100 million years after the Big Bang. This raises intriguing questions about how these supermassive black holes could have grown so quickly in the early universe. The rapid formation and growth of these objects suggests that they may have formed through processes that are still poorly understood. Did they begin as smaller black holes that grew over time? Or did they form through a more exotic process, such as the collapse of massive gas clouds in the early universe? Understanding the formation and growth of supermassive black holes is key to unlocking the mysteries of the early universe and the origins of galaxies. One area of active research involves the search for quasar analogues, objects that exhibit similar characteristics to double-lobed quasars but are much closer to us in terms of cosmic distance. By studying these analogues, astronomers hope to better understand the dynamics of quasar jets and their role in galaxy evolution. These objects could also provide a more detailed picture of the mechanisms that drive the energy output of quasars, which remains one of the most significant unanswered questions in astrophysics. In addition to studying distant quasars, astronomers are also focusing on the evolution of local quasars. While most quasars are located billions of light years away, a handful of quasars are relatively nearby, allowing for much more detailed observations. Studying these objects can help astronomers better understand the relationship between supermassive black holes and their host galaxies, as well as the impact of quasar jets on their immediate environments. Local quasars also provide an opportunity to observe the complex feedback loops between black holes, galaxies, and the intergalactic medium in real time. By observing both distant and local quasars, scientists hope to build a more comprehensive picture of how these objects evolve over time and how they influence their environments. The goal is to understand not only the behavior of supermassive black holes, but also the role they play in shaping the galaxies and large-scale structures that make up the universe. Continuing our deep dive into the world of double-lobed quasars, we now venture further into the realm of observational challenges that astronomers face when studying these enigmatic objects. Despite the vast technological advancements in observational equipment, studying double-lobed quasars presents a unique set of difficulties due to their extreme distances, energetic emissions, and the sheer scale of the phenomena involved. The high redshifts of distant quasars mean that the light reaching us has been stretched due to the expansion of the universe, causing these objects to appear dimmer and more distorted. This makes their observation a meticulous process, requiring powerful telescopes and advanced imaging techniques. To observe these far-flung quasars, astronomers rely on a variety of instruments, from ground-based radio telescopes to space-based observatories. One of the key instruments in studying quasars is the Very Large Array, VLA, located in New Mexico. The VLA consists of 27 radio antennas spread across a vast distance, allowing scientists to collect data with exceptional resolution and sensitivity. By focusing on the radio wavelengths emitted by the jets of double-lobed quasars, astronomers can gain detailed images of the lobes and their structure. The VLA's ability to capture the interaction between the jets and their environment has provided invaluable insights into the behavior of relativistic particles and the dynamics of these supermassive black holes. In addition to radio observatories, optical and infrared telescopes play a critical role in studying quasars, allowing scientists to observe the light emitted by the accretion disk around the black hole and the surrounding gas. One of the most famous optical telescopes, the Hubble Space Telescope, has captured stunning images of distant quasars and their surrounding regions, revealing the intricate structure of the jets and lobes. Hubble's resolution has allowed astronomers to study the complex interplay between the quasar's radiation and the gas in the host galaxy, shedding light on the mechanisms driving the quasar's extraordinary energy output. Yet, even with these powerful tools, the study of double-lobed quasars is far from straightforward. The process of interpreting the data is a monumental challenge. Quasar jets are highly dynamic and can change in intensity and structure over relatively short periods, sometimes in as little as a few years. This means that astronomers must take into account the evolving nature of the jets when attempting to understand their origin and behavior. Furthermore, the sheer complexity of the data collected from multiple wavelengths, radio, optical, infrared, X-ray, and even gamma rays, requires sophisticated models and computational simulations to piece everything together. Each quasar's jet is a puzzle of its own, with variations in the intensity of the emission, the direction of the jets, and the structure of the lobes. All these factors must be carefully analyzed in order to build an accurate model of the object's physical properties. The study of double-lobed quasars also faces cosmological challenges, as these objects are often located at such great distances that their light is subject to the distortions of the expanding universe. The redshift of light emitted by quasars means that by the time we observe them, they are no longer in the same state they were when they emitted their light. This introduces a level of uncertainty when trying to determine the current state of these objects, as the time it takes for light to travel across vast cosmic distances means we are seeing them as they were millions or even billions of years ago. To counter this, astronomers rely on spectroscopic redshifts, which allow them to determine how far away a quasar is by analyzing the light's wavelength. However, even with these techniques, measuring the exact distance to a quasar remains an ongoing challenge, and astronomers must often use a combination of methods to cross-check their results. One of the most fascinating aspects of studying double-lobed quasars is their role in the broader context of galaxy formation and evolution. While these quasars are undoubtedly some of the most energetic objects in the universe, they also play a significant role in the long-term development of galaxies. As we discussed earlier, the energy emitted by quasar jets can influence the host galaxy, potentially inhibiting star formation in certain regions. This phenomenon, known as feedback, is thought to be one of the key factors in the regulation of galaxy growth. The jets act as a kind of cosmic thermostat, preventing the overproduction of stars and stabilizing the galaxy's overall structure. Understanding how this process works is crucial for understanding the life cycle of galaxies, as it helps explain how galaxies evolve from early, chaotic star-forming regions to the more stable, quiescent galaxies we see today. Furthermore, the study of double-lobed quasars provides critical insights into the relationship between supermassive black holes and their host galaxies. These black holes, which can be millions or even billions of times the mass of the Sun, are thought to have formed in tandem with their host galaxies. The presence of a supermassive black hole at the center of a galaxy is thought to play a crucial role in shaping the galaxy's structure, influencing the distribution of gas and stars, and even determining the galaxy's overall shape. The jets emitted by quasars are an important manifestation of this relationship, as they serve as a direct link between the black hole and the galaxy's environment. By studying the properties of quasar jets and their interaction with the surrounding matter, astronomers can gain valuable insights into the processes that govern the formation and evolution of both galaxies and their central black holes. One particularly intriguing aspect of double-lobed quasars is the possibility that their jets may be related to the formation of large-scale cosmic structures. The energy and matter ejected by the quasar's black hole can extend far beyond the host galaxy, sometimes reaching across hundreds of thousands of light-years. This means that quasars have the potential to influence not only their host galaxy but also the entire galaxy cluster in which they reside. These jets could act as cosmic pumps, driving the movement of gas and dark matter across vast distances. As we continue to observe quasars and their jets, we may uncover new insights into the role that supermassive black holes play in shaping the structure of the universe on the largest scales. Another aspect that makes double-lobed quasars so intriguing is their potential for uncovering the nature of dark matter and dark energy. The powerful jets emitted by these objects create high-energy environments that could, in theory, reveal the presence of exotic forms of matter and energy. Dark matter, which makes up approximately 27% of the universe's mass energy content, cannot be observed directly, but its influence can be detected through its gravitational effects on visible matter. If we can understand how quasar jets interact with the surrounding dark matter, we might gain a better understanding of its properties and behavior. Similarly, the study of quasars could help us to learn more about dark energy, the mysterious force that is driving the accelerated expansion of the universe. At the heart of all of this research is the quest to answer some of the most profound questions in cosmology. How did supermassive black holes form? How do they grow and evolve over time? And how do their interactions with their host galaxies shape the universe as a whole? These questions are deeply intertwined with the study of double-lobed quasars, and by continuing to explore these objects, astronomers hope to uncover answers that will not only enhance our understanding of quasars but also help us to unlock the broader mysteries of the cosmos. The future of quasar research looks incredibly promising, as advancements in technology and new observational techniques will only deepen our understanding of these fascinating objects. In the coming decades, we can expect to see more detailed and high-resolution images of double-lobed quasars, as well as more precise measurements of their energy emissions and interactions with their environment. With the upcoming launch of new space telescopes, such as the James Webb Space Telescope, JWST, astronomers will be able to observe the universe in unprecedented detail, providing a clearer picture of quasars in the early universe and their role in shaping galaxies and large-scale structures. Double-lobed quasars are not just extraordinary cosmic objects, they are key pieces of the puzzle that will help us understand the universe's most fundamental processes. By studying these powerful jets and their interactions with the surrounding matter, we are learning about the evolution of galaxies, the behavior of supermassive black holes, and the cosmic forces that shape the universe on both small and large scales. The mysteries surrounding double-lobed quasars are far from being fully unraveled, and as technology advances, we are bound to uncover even more astonishing insights about these fascinating cosmic phenomena. As we continue our exploration of double-lobed quasars, it's important to dive deeper into how these objects influence not only their immediate surroundings but also the broader cosmic landscape. While much of the focus has been on the dynamics of the jets, another crucial aspect of these quasars is their interaction with the intergalactic medium, IGM. The IGM refers to the diffuse gas and matter that exists between galaxies, filling the vast stretches of space between the more compact, denser regions of the universe. Understanding how quasar jets interact with the IGM can provide us with valuable clues about the state of the universe during its formative years, especially in the epoch known as the Cosmic Dawn. During this period, the universe was still in its infancy, with the first stars and galaxies beginning to form and emit light. The energy from quasar jets could have played a significant role in reionizing the universe, a process that occurred about 1 billion years after the Big Bang. Reionization refers to the era when the gas in the universe, which was originally neutral, became ionized due to the intense radiation emitted by the first stars and quasars. The jets from double-lobed quasars likely contributed to this process, heating the surrounding gas and influencing the formation of large-scale structures. The feedback mechanism from the quasar jets may have also played a role in galaxy cluster evolution. As these jets expand outward, they interact with the gas in their host galaxy's cluster, heating it and preventing it from cooling down and condensing into new stars. This heating effect is known as thermal feedback, and it can have a significant impact on the rate of star formation in the cluster. In fact, studies have shown that the feedback from quasar jets may be responsible for suppressing star formation in the central regions of galaxy clusters, leading to the creation of so-called red and dead galaxies that are no longer forming stars but still contain large numbers of older, redder stars. This process is crucial for understanding the evolution of galaxy clusters over cosmic time. Interestingly, double-lobed quasars are not only key players in the formation of galaxies but also in the distribution of matter in the universe. The powerful outflows from quasar jets can influence the movement of gas and dark matter across vast distances, helping to shape the cosmic web, the large-scale structure that connects galaxies and clusters through vast filaments of dark matter and gas. As quasars emit these high-energy jets, they deposit energy into the surrounding gas, pushing it outward and triggering complex flows. These flows can contribute to the formation of voids in the cosmic web, regions where few galaxies are found, and may help explain the distribution of matter in the universe. Moreover, the study of quasar variability offers another fascinating avenue for understanding the processes occurring within these distant objects. While quasars are known for their remarkable brightness, they are also dynamic, with their luminosity fluctuating over time. These changes can occur on timescales ranging from hours to years, and astronomers have spent decades trying to understand the underlying mechanisms that cause such variability. The variability of a quasar is often related to the dynamics of the accretion disk around the supermassive black hole at its center. As matter falls onto the black hole, it heats up, emitting radiation across a wide range of wavelengths. However, these accretion processes are not always uniform, and sometimes instabilities can cause the brightness of the quasar to change abruptly. This phenomenon of quasar variability is particularly pronounced in double-lobed quasars, where the emission from the jets and lobes can also fluctuate, providing astronomers with additional clues about the inner workings of these enigmatic objects. To add to the complexity, some double-lobed quasars exhibit asymmetrical features in their jets and lobes. This asymmetry can be caused by several factors, including differences in the density of the surrounding gas, the orientation of the quasar's spin axis, or the presence of large-scale magnetic fields. In some cases, one lobe may appear much more pronounced or energetic than the other, leading to questions about the forces shaping these structures. For instance, the jet might be skewed or directed at an angle due to interactions with the surrounding medium or the gravitational influence of nearby objects. Understanding why these asymmetries exist could unlock further insights into the physics of black hole accretion and the behavior of relativistic jets. The quest to fully understand double-lobed quasars also intersects with one of the most intriguing areas of astrophysics: the potential for multi-messenger astronomy. Traditionally, astronomers have relied on electromagnetic waves, light, radio waves, X-rays, etc., to study distant objects. However, the advent of gravitational wave detectors and neutrino telescopes has opened up the possibility of studying the universe using different messengers. Gravitational waves, which are ripples in spacetime caused by the acceleration of massive objects, could provide a new way to probe the violent processes occurring in the centers of quasars. The possibility of detecting gravitational waves emitted by merging supermassive black holes in quasar systems is a tantalizing prospect that could revolutionize our understanding of these objects. In a similar vein, the detection of high-energy neutrinos, which are subatomic particles that interact only very weakly with matter, could provide critical insights into the processes happening in quasar jets. Neutrinos are produced in vast quantities by high-energy processes like the acceleration of particles in quasar jets. Their detection could reveal information about the jets that is otherwise inaccessible through conventional electromagnetic observations. As the sensitivity of neutrino telescopes improves, we may be able to observe these elusive particles and use them to trace the high-energy processes occurring in double-lobed quasars. As we look toward the future of quasar research, there are several exciting developments on the horizon. The upcoming generation of space observatories, such as the James Webb Space Telescope, JWST, promises to revolutionize our understanding of quasars and their environments. The JWST, with its powerful infrared capabilities, will be able to observe distant quasars in greater detail than ever before. This includes the ability to study the regions surrounding the jets, providing a clearer picture of how quasar jets interact with their environment and influence galaxy formation. Moreover, ground-based observatories are continuing to push the boundaries of what is possible with extremely large telescopes like the Extremely Large Telescope, ELT, and the 30-meter telescope, TMT. These telescopes, currently under construction, will offer unprecedented resolution and sensitivity, allowing scientists to study quasars in even greater detail. With these new instruments, we may be able to observe the fine structure of the jets and lobes, helping us to answer some of the most fundamental questions about the formation and evolution of quasars. In addition to observational advancements, theoretical research is also advancing rapidly. The development of numerical simulations of black hole accretion and jet formation is allowing scientists to test their hypotheses about quasar behavior in a more detailed and accurate way. These simulations, powered by cutting-edge supercomputers, are helping astronomers to better understand the complex dynamics of double-lobed quasars and make predictions about how they will evolve over time. With all these developments, one thing is certain: the study of double-lobed quasars will continue to be one of the most exciting and dynamic fields in astrophysics. As we push the boundaries of technology and refine our models of the universe, we will undoubtedly uncover new and unexpected insights about these remarkable objects. From their role in galaxy formation to their potential for unveiling the mysteries of dark matter and dark energy, double-lobed quasars remain at the forefront of cosmological research. Their study not only deepens our understanding of the universe but also fuels our curiosity about the origins of the most powerful phenomena in the cosmos. As we continue to unravel the complexities of double-lobed quasars, it's essential to consider the broader implications of their existence within the universe's larger evolutionary context. One of the key areas that benefit from the study of these quasars is our understanding of the large-scale structure of the universe. The influence of double-lobed quasars extends far beyond their immediate environment, reaching into the very fabric of the cosmic web that connects galaxies, galaxy clusters, and vast expanses of voids. The jets emanating from these quasars are not just energetic streams of particles. They also play a pivotal role in shaping the distribution of matter across cosmic distances. The jets, with their relativistic speeds, can trigger significant changes in the surrounding intergalactic medium, sometimes heating and displacing gas over massive scales. In this way, quasars may help explain the formation and evolution of superclusters, which are some of the largest structures in the universe. By interacting with the intergalactic gas, the jets from double-lobed quasars can prevent the cooling of this gas, thus hindering the formation of new galaxies. This process, known as feedback suppression, is believed to be one of the driving forces behind the creation of large, diffuse galaxy clusters that are seemingly quenched of star formation. Additionally, quasars contribute to the ongoing debates about the nature of dark energy. Dark energy is the mysterious force that appears to be accelerating the expansion of the universe, and understanding its influence is crucial for the future of cosmology. While the study of quasars in isolation may not directly provide answers about dark energy, the effects of quasar jets on the expansion and cooling of the universe's gas could offer indirect clues. If these jets are influencing the rate at which the universe cools and structures form, they may also be linked to the underlying forces that drive cosmic expansion. In terms of observational techniques, advancements in radio astronomy have provided crucial insights into the behavior of double-lobed quasars. The jets themselves are often most visible in the radio wavelengths, making this part of the electromagnetic spectrum invaluable for studying the structure of quasars. With radio interferometry, such as the Very Large Array (VLA) and the Event Horizon Telescope (EHT), astronomers can map the fine structure of quasar jets with unprecedented resolution, allowing us to better understand how these jets form and interact with their environment. The data gathered from such observations are critical for refining models of relativistic jets and the mechanisms driving their formation. One of the most significant challenges in quasar research is the redshift effect, which is particularly pronounced in distant double-lobed quasars. Due to the vast distances that these objects lie from Earth, the light emitted from them experiences a redshift, meaning that its wavelength is stretched as it travels toward us. This redshift can distort the appearance of the quasar and its jets, making it more difficult to study them accurately. However, this very same redshift provides us with a valuable tool for measuring the distance to these quasars, which in turn helps astronomers trace the history of the universe. The further away a quasar is, the older it is, meaning it offers a snapshot of the early universe and the conditions that existed billions of years ago. The study of double-lobed quasars, therefore, acts as a window into the universe's formative years. The relationship between black holes and quasars is another exciting avenue of exploration. We know that quasars are powered by the accretion of material around supermassive black holes. This relationship raises profound questions about the growth and evolution of these black holes and how they influence their host galaxies. In particular, astronomers have speculated about the potential connection between supermassive black hole mergers and the formation of double-lobed quasar systems. When two supermassive black holes within a galaxy merge, the resulting quasar may exhibit characteristics of double-lobed jets. The mechanics behind this phenomenon are still being debated, but the possibility that quasar jet formation could be influenced by the dynamics of black hole mergers is an exciting area of study. In addition to these fundamental questions, double-lobed quasars continue to present an opportunity to study extreme physics. For instance, the jets of these quasars are composed of highly energetic particles moving at relativistic speeds, close to the speed of light. The behavior of matter in these conditions challenges our understanding of special relativity, quantum mechanics, and magnetohydrodynamics. How do the magnetic fields generated by these black holes accelerate particles to such extreme velocities? How do these jets remain collimated over vast distances, often extending for millions of light years? The answers to these questions could revolutionize our understanding of physics at the most extreme scales. Moreover, double-lobed quasars may hold the key to understanding magnetic field generation in astrophysical systems. The interaction between accretion disks and jets often involves powerful magnetic fields that influence the behavior of charged particles. These magnetic fields are crucial for jet collimation, and studying the jets of quasars can give us insight into the processes that govern astrophysical magnetism. Recent studies have shown that the magnetic field structure in quasar jets is far more complex than previously thought, and understanding this complexity is central to understanding how relativistic jets are launched and maintained. As technology continues to advance, the tools available for studying double-lobed quasars are becoming more sophisticated. Next-generation telescopes, such as the Square Kilometre Array (SK), promise to revolutionize the study of these objects. The SK, a radio telescope currently under construction, will be able to survey the sky with unprecedented resolution and sensitivity. With its ability to detect faint radio emissions from distant quasars, the SK will provide astronomers with invaluable data to study the evolution of quasars, the formation of their jets, and their interactions with their environments. This will likely lead to major breakthroughs in our understanding of supermassive black holes and their role in shaping the universe. Another emerging technique in the study of double-lobed quasars is the use of machine learning. With the sheer volume of data generated by modern telescopes, traditional methods of data analysis are becoming increasingly insufficient. Machine learning algorithms are now being employed to analyze vast datasets and identify patterns that would otherwise be difficult to detect. These techniques can help astronomers identify new quasars, classify their properties, and even predict how their jets will behave. The use of artificial intelligence in astronomy is still in its infancy, but it holds the potential to greatly enhance our ability to study double-lobed quasars and other astrophysical phenomena. Looking further into the future, it is clear that the study of double-lobed quasars will continue to be a cornerstone of astrophysical research. Their unique characteristics, from their powerful jets to their complex interactions with the surrounding environment, make them key to understanding a wide range of processes in the universe. As we develop more advanced technologies and refine our theoretical models, our knowledge of these extraordinary objects will undoubtedly grow, offering us a deeper understanding of the universe's most extreme phenomena. The ongoing exploration of double-lobed quasars is not just about understanding these individual objects, but also about piecing together the grand narrative of the universe itself. By examining these distant, energetic objects, we can learn about the formation and evolution of galaxies, the behavior of matter in extreme conditions, and the forces that shape the cosmos. As we continue to study quasars and other high-energy astrophysical phenomena, we edge ever closer to answering some of the most profound questions about the nature of the universe and our place within it. The study of double-lobed quasars also touches on more philosophical questions about the universe. These quasars, with their vast energy output and extreme environments, challenge our understanding of the laws of nature. For instance, the sheer scale of these cosmic phenomena forces us to reconsider our perception of the universe's limits. How can such a small, compact object, albeit incredibly massive, be capable of producing jets that extend across millions of light years? What does this say about the scale of the universe, and our place within it? Double-lobed quasars are an example of how the cosmos consistently pushes the boundaries of what we think we know, forcing us to continually adjust our models and theories. Moreover, the study of double-lobed quasars contributes to our understanding of cosmological evolution. These objects are ancient, often seen as they existed billions of years ago, when the universe was much younger. By studying quasars at different redshifts, we gain insight into how the early universe functioned. This knowledge is crucial in piecing together the timeline of the universe's formation and evolution. For instance, how did the very first quasars come into being? Were they the products of the early universe's chaotic and violent processes? Or do they represent a more stable phase in cosmic history? These questions help bridge the gap between theoretical cosmology and observational astronomy. The impact of double-lobed quasars extends even beyond our understanding of astrophysics. Their study informs the field of extraterrestrial intelligence, ETI, and the search for life beyond Earth. The enormous power output of quasars raises the possibility that such energy sources could have implications for habitable environments elsewhere in the universe. If quasars can impact the evolution of their host galaxies, they could play a role in shaping the conditions required for life to emerge on distant planets. Additionally, the study of quasar jets and their ability to influence the surrounding environment could provide clues about the types of energy signatures that might be detectable by future missions looking for signs of advanced civilizations. In the realm of technology, the study of double-lobed quasars has driven advancements in computational methods and modeling techniques. The complex processes involved in the formation and behavior of quasar jets require simulations that incorporate a range of physical phenomena, from general relativity to fluid dynamics and magnetohydrodynamics. These simulations are often run on some of the world's most powerful supercomputers, pushing the limits of computational physics. As a result, the study of quasars has led to improvements in numerical relativity and other computational techniques that are now applied to a range of scientific fields, including climate modeling and nuclear fusion research. Furthermore, quasars continue to inspire the imagination and curiosity of people around the world. Their spectacular displays of energy remind us of the sheer majesty and mystery of the cosmos. In many ways, quasars, including double-lobed types, serve as symbols of the unexplored frontier, representing the unknown and the yet-to-be-understood. As we delve deeper into their study, we are not only advancing our knowledge of the universe but also satisfying our innate curiosity about the great questions of existence. Where did the universe come from? How did it evolve into its current state? And what mysteries lie ahead, waiting to be uncovered? Perhaps one of the most fascinating aspects of double-lobed quasars is the interdisciplinary nature of their study. While they are primarily objects of interest to astronomers and astrophysicists, quasars also have connections to fields as diverse as mathematics, philosophy, and even art. The mathematical models that describe quasar jets, for instance, require a deep understanding of advanced geometry, topology, and calculus. In a philosophical sense, quasars raise questions about the nature of existence and the forces that shape the cosmos. And from an artistic perspective, their immense energy and cosmic scale have inspired numerous works of science fiction, art, and popular media. One potential avenue for future exploration is the connection between quasars and the cosmic microwave background, CMB. The CMB is a remnant of the early universe, providing us with a snapshot of the universe's conditions just after the Big Bang. The interaction between the energy released by quasars and the CMB could reveal important information about the evolution of the universe and the role quasars played in shaping the early cosmos. This is an area of active research, with astronomers exploring how high-energy objects like quasars and gamma-ray bursts might have contributed to the ionization and thermal history of the universe. The technological innovations spurred by the study of quasars also have broader applications. For example, the development of more advanced radio telescopes and imaging techniques used to study double-lobed quasars has led to advancements in communication technology. The principles behind radio wave propagation and the handling of large datasets in quasar studies have inspired improvements in satellite communication systems, broadband internet, and even radar technologies. The techniques that allow scientists to observe quasars in such detail can be adapted to solve practical problems here on Earth. We must consider the implications of studying double-lobed quasars for future space exploration. The extreme environments found around these objects can teach us about the limits of space travel and the kinds of challenges that future explorers might face when venturing into the deepest parts of the universe. Whether it's the effects of high-energy radiation, the influence of supermassive black holes, or the mechanics of relativistic jets, the lessons learned from quasars could help prepare humanity for future missions beyond our solar system. As we look forward to further exploration of double-lobed quasars, there is no doubt that these objects will continue to be at the forefront of astrophysical research. With each new discovery, we gain a deeper understanding of the fundamental forces that govern the universe and the role that quasars play in shaping the cosmos. By studying these extraordinary phenomena, we are not just learning about distant objects in space. we are also learning about the very nature of the universe itself. The journey of discovery is far from over, and with each new breakthrough, we move closer to unraveling the mysteries of the cosmos, one quasar at a time. As we move deeper into the exploration of double-lobed quasars, one aspect that requires further investigation is the role of feedback mechanisms within the host galaxies. These mechanisms are responsible for regulating the growth of galaxies, particularly in how energy and matter are exchanged between the black hole at the center and the rest of the galaxy. In the case of double-lobed quasars, the jets emanating from the supermassive black hole can have a profound effect on their host galaxy, influencing star formation and the distribution of gas and dust within the galaxy. The interaction between the quasar's jets and the surrounding medium is a critical factor in understanding the evolution of galaxies. For instance, the energy released by the jets can prevent gas from cooling and condensing, a process crucial for the formation of new stars. This feedback loop can either promote or suppress star formation, depending on the intensity and duration of the quasar's activity. In some cases, the quasar may blow away the gas necessary for new stars to form, leading to a suppression of star formation in the galaxy. In other cases, the outflow from the quasar may help trigger new star formation by compressing gas clouds. This dynamic relationship between the quasar and its host galaxy is an area of ongoing research and could provide valuable insights into the broader processes of galaxy evolution. In addition to feedback mechanisms, the study of double-lobed quasars also ties into the evolution of the supermassive black holes at their centers. Supermassive black holes, typically millions to billions of times the mass of the Sun, are a central feature of quasars. These objects are thought to form during the early stages of galaxy development, growing by accreting material from their surroundings. The growth of these black holes and the corresponding formation of quasars may have played a crucial role in shaping the large-scale structure of the universe. Understanding how black holes grow and evolve, especially in the context of double-lobed quasars, could reveal much about the early universe and the processes that led to the formation of galaxies and clusters of galaxies. A fascinating possibility arises when considering the relationship between double-lobed quasars and dark matter. Dark matter, the mysterious substance that makes up a significant portion of the universe's mass, has long been a subject of intrigue in cosmology. While we cannot directly observe dark matter, we infer its presence based on its gravitational effects on visible matter, such as galaxies and clusters of galaxies. Some theories suggest that quasars, through their immense gravitational influence, may interact with or even be influenced by dark matter. For example, the gravitational fields of quasars could potentially have an effect on the distribution of dark matter in their host galaxies or in the surrounding region. Investigating this connection between quasars and dark matter is an exciting frontier in astrophysics, as it could provide a more complete understanding of the forces that govern the structure and evolution of the universe. In recent years, advances in observational technology have allowed scientists to study quasars with unprecedented precision. Instruments such as the Atacama Large Millimeter Array, ALMA, and the Event Horizon Telescope, EHT, have made it possible to observe quasars in a variety of wavelengths, from radio to X-rays. These observations have provided new insights into the structure of quasar jets and the processes occurring in the accretion disk surrounding the black hole. For example, ALMA has been instrumental in observing the molecular gas surrounding quasars, shedding light on how this gas feeds into the black hole and how it interacts with the outflows from the quasar. Similarly, the EHT's ability to capture images of black holes has given astronomers a better understanding of the dynamics of the accretion disk and the relativistic jets. With these new technologies, the study of double-lobed quasars has entered a new era. Researchers are now able to map the jets in greater detail, observing their interactions with the surrounding environment, and studying their role in the evolution of galaxies. By combining data from multiple wavelengths of light, scientists can construct more accurate models of how quasars evolve and how their energy output affects their host galaxies and the broader universe. The study of double-lobed quasars is also contributing to our understanding of high-energy astrophysics. Quasars are among the most energetic objects in the universe, with their jets often emitting radiation across the entire electromagnetic spectrum. This makes them ideal laboratories for studying extreme physical processes, such as relativistic effects, magnetic fields, and high-energy particle acceleration. For example, the relativistic jets of quasars provide an opportunity to study the behavior of matter and radiation in the presence of strong gravitational fields. These studies are essential for testing and refining our understanding of general relativity, one of the foundational theories of modern physics. Moreover, the study of quasar jets helps astrophysicists better understand how cosmic rays, high-energy particles traveling at nearly the speed of light, are accelerated to such extreme velocities. One particularly intriguing aspect of quasar jets is their potential role in the formation of large-scale cosmic structures. The immense energy released by quasars can have a far-reaching impact on their surroundings, influencing the behavior of galaxies and even galaxy clusters. In some cases, the energy from the jets can heat up and expel gas from the galaxy, preventing the formation of new stars. In other cases, the energy from the quasar can compress gas clouds, triggering new waves of star formation. This feedback loop can have a significant impact on the evolution of galaxies, helping to shape the overall structure of the universe. The role of double-lobed quasars in cosmic evolution also extends to the study of galaxy clusters. Quasars are often found in the centers of galaxy clusters, and their powerful jets can have a profound impact on the evolution of the entire cluster. By interacting with the gas and dust in the cluster, quasar jets can influence the rate of star formation and the distribution of matter within the cluster. Understanding how quasars affect galaxy clusters is crucial for developing a complete picture of how large-scale cosmic structures form and evolve over time. As the field of extraterrestrial intelligence, ETI, continues to evolve, the study of double-lobed quasars may also provide insights into the search for life beyond Earth. The immense energy output of quasars and the potential influence of their jets on nearby galaxies could have implications for the conditions required for life to emerge on distant planets. For example, if quasars are capable of shaping the environments of their host galaxies, they may also be responsible for creating the conditions necessary for habitable zones on planets in those galaxies. This connection between quasars and the potential for life in the universe adds an intriguing layer to our ongoing exploration of the cosmos. In the coming years, we can expect even more breakthroughs in the study of double-lobed quasars. As our observational tools become more advanced and our theoretical models more sophisticated, we will continue to uncover the mysteries surrounding these fascinating objects. With each new discovery, we move closer to understanding the fundamental processes that govern the universe and the role that quasars play in shaping the cosmos. The journey to unlock the secrets of double-lobed quasars is far from over, and with it comes the promise of new insights into the very nature of reality itself. As we continue to delve into the mysteries of double-lobed quasars, another critical aspect that deserves attention is the variation in the appearance and behavior of these objects. Not all double-lobed quasars are the same, and their jets can exhibit significant differences in terms of size, direction, and energy. Some quasars feature well-defined lobes that extend far beyond the host galaxy, while others have more compact or distorted structures. Understanding the reasons behind these variations is a crucial part of studying quasars, as it could shed light on the underlying physical processes that govern the formation of these enormous and energetic phenomena. One factor that may contribute to these differences is the orientation of the quasar relative to the observer. Depending on the angle at which we observe the quasar, the jets may appear elongated and symmetrical, or they may appear more diffuse and distorted. This phenomenon, known as Doppler boosting, occurs because the light emitted by the jets is amplified when we view them along their direction of travel. In contrast, when the jets are oriented away from us, the light is dimmed, and the structure may appear more chaotic or less pronounced. This difference in appearance due to the orientation of the jets can make it challenging for astronomers to accurately assess the true shape and extent of a quasar's lobes. However, with the advancements in observational techniques, astronomers are increasingly able to overcome these challenges and obtain more accurate measurements of quasar structures, regardless of orientation. Another key factor influencing the structure of double-lobed quasars is the density and distribution of the surrounding medium. The jets from a quasar interact with the gas and dust in their environment, shaping the lobes as they expand outward. In regions where the gas is dense, the jets may slow down or compress, leading to the formation of more tightly defined lobes. Conversely, in areas with less gas, the jets may spread out more freely, resulting in larger, more diffuse lobes. These interactions between the quasar jets and the surrounding medium are complex and depend on various factors, such as the temperature and pressure of the gas, the magnetic fields in the region, and the velocity of the jets. Understanding how these factors come together to shape the lobes of quasars is essential for building a comprehensive model of quasar behavior and evolution. It is also important to consider the role of magnetic fields in the formation and behavior of double-lobed quasars. Magnetic fields are thought to play a significant role in the collimation and acceleration of the jets emanating from the black hole. These magnetic fields can help guide the jets, ensuring that they maintain their structure as they travel through space. Additionally, the strength and configuration of the magnetic fields can influence the morphology of the lobes themselves. In some cases, magnetic fields may cause the jets to twist or bend, creating asymmetric lobes. In other cases, the magnetic fields may help focus the jets, leading to more well-defined, symmetrical lobes. By studying the magnetic properties of quasars, scientists can gain valuable insights into the mechanisms that drive their jet formation and behavior. The study of double-lobed quasars also raises important questions about the life cycle of quasars. Quasars are thought to be an active phase in the evolution of certain galaxies, fueled by the accretion of material into a supermassive black hole. Over time, however, the activity of a quasar can subside as the black hole exhausts its supply of material or as external factors, such as feedback from the surrounding galaxy, disrupt the accretion process. This leads to the question of how quasars transition from their active, luminous state to a more quiescent phase. One possibility is that the jets from the quasar may gradually lose their energy, causing the lobes to shrink or become less distinct. Alternatively, the quasar may experience periods of intense activity followed by dormancy, creating a more cyclical pattern of behavior. Understanding the life cycle of quasars, particularly double-lobed ones, is crucial for our understanding of the evolution of galaxies and the role of black holes in shaping cosmic structures. Furthermore, the study of double-lobed quasars has important implications for our understanding of the cosmic distance scale. Because quasars are so luminous, they can be observed at vast distances, making them valuable tools for measuring the size and age of the universe. By studying the light emitted by quasars and analyzing the redshift of their spectra, astronomers can determine how far away these objects are and how the universe has expanded since their light was emitted. This information helps refine our models of cosmology and provides crucial insights into the history and evolution of the universe. In particular, double-lobed quasars, with their bright and well-defined jets, serve as excellent indicators of the universe's expansion and the large-scale structure of space. One of the most exciting prospects in the study of double-lobed quasars is the potential for multi-messenger astronomy. This relatively new field involves the use of multiple types of observational data, such as gravitational waves, electromagnetic radiation, and neutrinos, to study astronomical phenomena. By combining observations from different types of messengers, scientists can gain a more complete and nuanced understanding of quasars and their environments. For example, gravitational wave detectors, such as LIGO, could potentially detect signals from supermassive black hole mergers that occur in quasar-hosting galaxies. These mergers may be accompanied by the release of high-energy radiation that could be observed by traditional telescopes, providing a unique opportunity to study the behavior of double-lobed quasars in unprecedented detail. Similarly, neutrino observatories may provide valuable information about the high-energy processes occurring in quasar jets. The combination of these different forms of data could revolutionize our understanding of quasars and their role in the universe. Another exciting development in quasar research is the potential for the discovery of new types of quasars. Although double-lobed quasars are among the most well-known and studied, there is still much to learn about the variety of quasar types that exist across the cosmos. For instance, some quasars may feature multiple lobes, or exhibit unusual jet structures that don't fit the typical double-lobed model. Others may exist in environments that are very different from the typical galactic hosts of quasars. As observational techniques improve and we gain access to new, more powerful telescopes, it is likely that astronomers will discover entirely new classes of quasars, each with its own unique characteristics and mysteries. These discoveries could offer fresh insights into the diversity of supermassive black holes and the wide range of conditions that allow quasars to form and evolve. Furthermore, the study of double-lobed quasars provides important clues about the history of the universe. The light emitted by quasars travels vast distances before reaching our telescopes, allowing us to observe objects as they were billions of years ago. This means that by studying the properties of distant quasars, we can gain insights into the conditions that existed in the early universe. Double-lobed quasars, with their powerful jets and unique structural features, may hold key information about the processes that led to the formation of the first galaxies, stars, and black holes. By piecing together the puzzle of quasar evolution, we can learn more about how the universe has changed over time and how the building blocks of galaxies and clusters were laid down. Double-lobed quasars are among the most fascinating and enigmatic objects in the universe. From their powerful jets and intricate structures to their potential role in galaxy evolution and cosmic feedback mechanisms, these objects offer a wealth of opportunities for scientific discovery. As our observational tools continue to improve and our understanding of the physics behind quasars deepens, we are bound to uncover even more mysteries about these extraordinary phenomena. Whether they are shaping the galaxies they inhabit, providing insights into the distant past, or influencing the large-scale structure of the universe, double-lobed quasars remain a captivating area of study for astronomers and astrophysicists alike. As we continue to explore the world of double-lobed quasars, another intriguing aspect lies in the variety of energy sources that fuel these cosmic giants. The energy emitted by a double-lobed quasar is primarily a result of the interaction between the material falling into the supermassive black hole at the center of the quasar and the intense gravitational forces at play. As this material spirals inward, it heats up to extreme temperatures and releases vast amounts of energy, which is then channeled into the powerful jets that extend outward from the black hole. However, what's particularly fascinating is the way these energy sources are not uniform across all quasars, leading to unique patterns in the formation and intensity of the lobes. A key factor in understanding the energy output of double-lobed quasars is the accretion disk. This disk of gas, dust, and other debris surrounds the black hole, slowly spiraling inward as it is drawn in by the black hole's immense gravity. The material in the accretion disk heats up to millions of degrees, emitting radiation in the form of X-rays, ultraviolet light, and sometimes visible light. This radiation is not only a result of the friction and collisions between particles in the disk, but also the release of gravitational potential energy as the material falls toward the black hole. In some cases, the accretion disk itself can become incredibly luminous, making the quasar one of the brightest objects in the universe. As the energy from the disk is transferred into the jets, it can fuel the powerful lobes, extending them over vast distances. It's also important to consider the role of feedback mechanisms in shaping the lobes of double-lobed quasars. As the supermassive black hole at the center of the quasar consumes matter from its surroundings, it generates immense amounts of energy, which can then interact with the surrounding environment. This interaction can lead to a process known as active galactic nucleus (AGN) feedback, in which the energy released by the quasar's jets can influence the formation of stars, the distribution of gas, and the overall evolution of the host galaxy. Essentially, the quasar's energy output has the potential to turn off star formation by heating the surrounding gas and preventing it from cooling down enough to form new stars. This feedback mechanism is a crucial aspect of galaxy evolution, as it may determine the rate at which galaxies grow and change over time. What's more, this feedback process can also play a role in the formation of the radial lobes seen in many double-lobed quasars. The jets from the quasar's central black hole are not simply streams of particles traveling through empty space. Rather, they interact with the surrounding medium, creating shock waves and turbulence that can expand the lobes. These lobes are typically filled with relativistic plasma, supercharged particles traveling at nearly the speed of light, which are energized by the quasar's central engine. The shape and size of the lobes depend on the density and temperature of the surrounding gas, the energy of the jets, and the magnetic fields at play in the region. The interaction between these factors leads to the characteristic double-lobed appearance of many quasars. Interestingly, the size of the lobes can vary dramatically from one quasar to another. In some cases, the lobes extend millions of light-years away from the central black hole, while in other cases, they are much smaller in size, perhaps only stretching tens of thousands of light-years. The size of the lobes is often determined by the amount of energy released by the quasar, as well as the density and properties of the surrounding medium. For example, quasars located in regions with dense gas and dust may produce smaller, more confined lobes, while those in less dense regions may have larger, more diffuse lobes. The dynamics of these jets are also crucial to understanding the mechanics of double-lobed quasars. The jets are often made up of a combination of high-energy particles and intense magnetic fields, which work together to accelerate and direct the outflowing material. The relativistic jets that emerge from quasars are capable of carrying enormous amounts of energy, traveling at speeds close to the speed of light. This allows them to shape their environment, creating large cavities in the surrounding gas and even heating it up to temperatures so high that star formation is inhibited. These jets can extend far beyond the host galaxy, with some of the largest quasars having jets that stretch millions of light-years across space. One question that has intrigued astronomers for decades is the origin of the jets themselves. How do the black holes at the center of these quasars generate such powerful outflows? A leading hypothesis is the Blandford's-Nagic mechanism, which suggests that the energy needed to power the jets is extracted from the black hole's spinning magnetic field. According to this theory, the rotation of the black hole generates a magnetic field that carries energy away from the black hole's event horizon. This energy is then transferred to the surrounding accretion disk, causing the material to accelerate and form the jets. The strength of the jets is thought to be directly related to the rate at which material falls into the black hole, with more rapid accretion leading to more powerful jets. Interestingly, the formation of double-lobed quasars is also influenced by the alignment between the jets and the host galaxy's structure. In some cases, the jets may be aligned in such a way that they extend directly outward from the center of the galaxy, creating well-defined, symmetric lobes. In other instances, the jets may be misaligned, resulting in more irregular or distorted lobes. This misalignment can occur due to a variety of factors, such as the orientation of the black hole within its host galaxy, interactions with neighboring galaxies, or gravitational influences from nearby massive objects. As a result, the lobes of double-lobed quasars can exhibit a wide range of shapes and configurations, from neatly symmetrical to highly distorted. The discovery of young, radio-loud quasars has added a new layer of complexity to our understanding of double-lobed quasars. These objects, known as young radio galaxies, are in the early stages of their life cycle, and their jets are still forming. As these young quasars evolve, the lobes they produce are often smaller and more compact compared to those of older quasars. This has led astronomers to propose that quasars may undergo significant changes in their jet structures as they age. Over time, the jets may expand and evolve into the more characteristic double-lobed shape, eventually becoming large enough to influence the entire host galaxy. The study of young radio galaxies is providing important clues about the early stages of quasar evolution and the factors that contribute to the formation of their powerful jets. In addition to providing valuable information about quasar evolution, double-lobed quasars also have implications for the study of dark matter and galaxy formation. Because quasars are located at the centers of galaxies, they can provide insights into the gravitational dynamics of these massive cosmic structures. In particular, the behavior of the jets and the lobes they create can reveal information about the distribution of mass within a galaxy, including the presence of dark matter. Dark matter is thought to make up a significant portion of the mass in the universe, but its exact nature remains one of the greatest mysteries in astrophysics. By studying the way that quasars interact with the surrounding matter, scientists hope to uncover more about the role of dark matter in shaping the formation and evolution of galaxies. The exploration of double-lobed quasars is also closely tied to the study of high-energy astrophysics. Quasars are among the most energetic objects in the universe, emitting vast amounts of radiation across the electromagnetic spectrum. This includes everything from visible light and ultraviolet radiation to X-rays and gamma rays. The study of these high-energy emissions is essential for understanding the physical processes occurring within the quasar itself, as well as the environment surrounding it. By observing the radiation emitted by quasars, astronomers can learn about the temperature, density, and composition of the material in the accretion disk, as well as the mechanisms that drive the powerful jets. As technology continues to improve, new observational techniques will allow us to probe quasars with greater precision. Instruments such as the James Webb Space Telescope, JWST, which is set to launch in the near future, will be able to observe quasars at unprecedented levels of detail, providing new insights into their structure, behavior, and evolution. These advancements will not only help us better understand double-lobed quasars but also revolutionize our knowledge of the universe as a whole. In the coming years, astronomers will continue to push the boundaries of what we know about these incredible objects. As we gain new insights into the formation of their jets, the structure of their lobes, and the way they interact with their environments, we will be better equipped to answer some of the most profound questions in modern astrophysics. As the supermassive black hole at the center releases energy through its jets, it doesn't just affect the immediate vicinity. It can dramatically influence the entire host galaxy and even its surrounding intergalactic environment. These feedback processes occur in a variety of forms, with some of the most significant involving thermal, mechanical, and radiative energy being dumped into the surrounding medium. This input of energy can regulate star formation, either by heating and expelling the gas that would otherwise condense into stars or by compressing gas clouds in a way that initiates starbirth. This balance between suppression and stimulation of star formation is one of the most delicate and crucial aspects in the study of galactic evolution. One of the more subtle outcomes of this process is what's referred to as maintenance mode feedback, where the jets from the black hole keep the surrounding hot gas in a state that prevents it from cooling and forming stars. This is especially common in massive elliptical galaxies, where the black hole's activity is thought to prevent the galaxy from becoming overly star-forming and instead maintain its older, redder stellar population. In contrast, there is also quasar mode feedback, associated with more dramatic and energetic outbursts that can blow away the gas in the central regions entirely, essentially halting star formation almost immediately. Double-lobed quasars, due to their immense power, are often associated with this latter type of feedback, although in practice, the line between these modes is not always clearly defined. As our instruments grow more sophisticated, astronomers have begun to detect double-lobed quasars at a wide range of redshifts, some relatively nearby, others at cosmological distances that date back to when the universe was just a few billion years old. These distant examples are particularly valuable because they offer a direct glimpse into the early phases of galaxy and black hole coevolution. By studying them, scientists can begin to map out how the first massive black holes formed, how they interacted with their environments, and how they shaped the large-scale structure of the universe. Spotting double-lobed quasars at such early epochs means that supermassive black holes and their jet-producing mechanisms were already in place not long after the Big Bang. These early quasars challenge models of black hole formation and growth, as it is still unclear how such massive objects could form so quickly within the timeline of cosmic history. Their presence suggests that either black holes formed through more massive initial seed mechanisms than previously thought, or that they grew at extraordinarily rapid rates in environments that were especially conducive to accretion. The ability to detect double-lobed quasars from so far away also underscores the importance of radio astronomy in modern astrophysics. Unlike visible light, radio waves are not easily absorbed or scattered by interstellar dust, which means that radio telescopes can peer deeper into the obscured regions of the cosmos. This gives astronomers a unique window into the behavior of distant quasars and allows for detailed studies of their jet structures and energy distributions. Instruments like the Very Large Array, VLA, and the Square Kilometer Array, SKA, are specifically designed to capture the extended lobes and faint emissions that define these extraordinary objects. As radio maps of the sky continue to improve, so does our catalog of known double-lobed quasars. Surveys such as FIRST, faint images of the radio sky at 20 centimeters, and LOFAR, low-frequency array, have revealed thousands of radio-loud quasars, many with double-lobed features. These surveys provide a statistical basis for examining how common these objects are, how they evolve, and how their lobes interact with their environments. Patterns begin to emerge. Certain environments seem more favorable to the development of large lobes, suggesting a dynamic relationship between quasars and the cosmic web. A fascinating phenomenon linked to these lobes is the creation of giant radio galaxies, where the lobes stretch across millions of light years, sometimes larger than the galaxies themselves. These giant structures suggest that the jets and lobes are long-lived and can remain active or visible even after the central quasar has gone quiet. Their immense scale makes them valuable markers for probing intergalactic medium conditions, as the expanding lobes interact with cosmic gas, revealing density fluctuations and magnetic field structures over colossal distances. Magnetic fields themselves are an essential component in the study of quasar lobes. The jets are thought to be highly magnetized, and the structure and orientation of these magnetic fields influence how the lobes grow and evolve. Polarization measurements in radio frequencies allow astronomers to map these fields, and through such studies, it's been discovered that the magnetic fields often align with the jet axis near the quasar's core, but become more chaotic in the extended lobes. This transition may reflect the gradual energy loss and turbulent mixing that occurs as the jets deposit their energy into the surrounding space. Energy loss in the lobes is also observed through synchrotron aging, a process where high-energy electrons gradually lose their energy as they emit radiation while spiraling through magnetic fields. This energy loss can be detected through changes in the radio spectrum, with older lobes appearing redder in radio wavelengths. By measuring the spectral index, the steepness of the radio emission, scientists can estimate the age of the lobes and, by extension, the active lifetime of the quasar's jet activity. Some lobes are only a few million years old, while others persist for hundreds of millions of years, revealing just how long these structures can remain after the quasar fades. In addition to energy loss, the shape and orientation of the lobes can reveal complex interactions with the surrounding environment. When a lobe encounters a dense region of intergalactic gas, it may slow down, become distorted, or even split apart. These environmental effects can be seen in head-tail radio sources, where one lobe is sharply bent due to movement through the intergalactic medium, often within clusters of galaxies. These interactions give clues not only about the quasar's own behavior, but also about the large-scale structure and dynamics of the universe. Some double-lobed quasars also show signs of episodic activity, where a black hole periodically turns its jets on and off. In such systems, double radio galaxies can appear, featuring two sets of lobes aligned along the same axis, with an older, faded pair flanking a newer, more active one. These galaxies suggest that black hole activity can be recurrent and that the fueling of the central engine may happen in bursts, potentially triggered by interactions with other galaxies, inflows of gas, or internal galactic dynamics. The process of galactic mergers is another major contributor to quasar activity. When two galaxies collide, their central black holes can eventually merge, and the influx of gas stirred up by the collision can fall into the black hole, igniting quasar activity. These interactions often leave behind chaotic environments that feed the black hole and may result in the launch of new jets. Double-lobed quasars arising from such events might exhibit asymmetries in their lobe structures or show signs of jet precession, where the direction of the jets slowly changes over time. Jet precession itself is a remarkable phenomenon, and is thought to result from binary black hole systems or from the influence of misaligned accretion disks. As the orientation of the disk shifts due to gravitational torques, the direction of the jets may also change, leading to S-shaped lobes or other complex morphologies. Observing and modeling such structures allows astronomers to infer the presence of unseen black hole companions and to reconstruct the dynamic history of these massive systems. The connection between double-lobed quasars and the broader cosmic structure is another compelling area of research. As jets extend outward, they don't just interact with isolated regions of gas, they encounter filaments, voids, and the edges of galaxy clusters. By mapping where these lobes are found and how they're shaped, researchers can learn about the distribution and properties of matter on the largest scales. Double-lobed quasars thus act as probes of the cosmic web, helping to fill in the gaps in our understanding of the large-scale universe. There's also a significant role played by X-ray observations in understanding the dynamics of these systems. Instruments like Chandra and XMM Newton have captured X-ray emissions from the hot gas shocked by the expanding radio lobes. These emissions provide a different view of the same structures visible in radio wavelengths, allowing astronomers to study the temperature, density, and composition of the gas being displaced and heated by the quasars' outbursts. When combined with optical and infrared data, these observations paint a comprehensive picture of how powerful jets can shape galactic ecosystems. On a more theoretical level, studying double-lobed quasars feeds into models of galaxy evolution. The interplay between black hole activity, jet feedback, and star formation regulates how galaxies grow over billions of years. Without such feedback, simulations suggest that galaxies would form too many stars too quickly, resulting in unrealistic galactic populations. Double-lobed quasars, through their intense outflows and massive energy input, play a central role in keeping this process in balance. And yet, despite decades of study, many questions remain unanswered. What exactly determines whether a quasar will produce jets at all? Why do only a fraction of them develop double-lobed structures? What causes some to remain active for hundreds of millions of years, while others shut off quickly? Answering these questions will not only deepen our understanding of quasars themselves but also illuminate the fundamental workings of the universe on both small and large scales. The extent of these lobes is another subject of intense fascination. Some double-lobed quasars possess jets that stretch across millions of light-years, effectively making them some of the largest single structures in the known universe. These gargantuan lobes are not only awe-inspiring in their sheer scale, but they also serve as crucial indicators of the dynamics at the heart of the quasar and the properties of the intergalactic medium through which they propagate. By studying their size, shape, and alignment, researchers can reverse engineer the physical conditions of the jet's origins and the environment they pass through. What makes these lobes even more intriguing is their remarkable symmetry in many cases. While not perfect, the two opposing jets often extend to roughly equal distances from the central quasar, suggesting an impressively stable and sustained energy output from the supermassive black hole. This symmetry implies a level of internal regulation and consistency in the black hole's accretion process and magnetic field structure over immense timescales. Deviations from symmetry, on the other hand, can indicate interaction with external forces, such as galaxy mergers, local density variations in the intergalactic medium, or turbulence caused by cosmic flows. One might imagine these colossal lobes as being relatively static, but they are in fact incredibly dynamic. The jets themselves are traveling near the speed of light, and while the visible lobes appear to be stationary due to the vast distances involved, their internal particles are in constant motion. Shock fronts, turbulence, and instabilities form and dissipate over time. These internal motions can be studied using radio frequency variations and time-lapse imaging across decades, revealing insights into the life cycle and decay of relativistic jets. Another key feature often observed in double-lobed quasars is the presence of hotspots at the ends of the jets. These are the regions where the jet material, moving at relativistic speeds, slams into the surrounding medium and abruptly slows down, transferring energy into the intergalactic gas. These hotspots shine brightly in radio and X-ray frequencies and often serve as the termination points of the lobes. Their structure and intensity can help astronomers understand the density and composition of the surrounding medium, as well as the momentum and energy of the jets themselves. The core-jet lobe structure of double-lobed quasars has become a textbook example of astrophysical jet systems. At the center lies the bright quasar core, home to the supermassive black hole and the accretion disk. From there, collimated jets of relativistic particles extend outward, creating the lobes as they plow through space. In many cases, a knotty appearance can be seen along the jets, where regions of shock or increased emission appear at regular intervals. These knots may be caused by periodic bursts from the central engine, interactions with external gas, or magnetic reconnection events within the jet flow itself. Interestingly, not all jets are perfectly straight. Some exhibit bends, twists, or corkscrew patterns, which can be caused by a variety of mechanisms. The motion of the host galaxy, precession of the black hole, or even binary black hole systems can cause the jet to curve or change direction over time. In extreme cases, the interaction with another galaxy's gravity can distort the jets, creating asymmetrical or S-shaped lobes that provide additional clues about the past interactions and movement history of the quasar. Beyond morphology, the spectral properties of the lobes reveal much about the aging process of the relativistic particles. As particles radiate energy, especially via synchrotron radiation, they lose energy over time. This leads to a steepening of the radio spectrum, an effect known as spectral aging. By studying this effect, astronomers can estimate how long the lobes have been active and how far the jet material has traveled. These measurements contribute to building a timeline of activity for the central black hole and understanding the duty cycle of quasar jet production. Another layer of complexity comes from the polarization of the radio emission. When charged particles spiral around magnetic field lines, the emitted radiation becomes polarized. Mapping the polarization vectors across the lobes reveals the underlying magnetic field structure, which in turn provides information about the formation and stability of the jets. In many double-lobed quasars, the polarization data show highly ordered fields, supporting the idea of coherent, large-scale magnetic structures guiding the flow of particles over immense distances. These insights become even more valuable when compared with simulations of jet formation and propagation. Using powerful supercomputers, astrophysicists have developed detailed models that simulate the behavior of relativistic jets in various environments. These simulations include factors such as magnetohydrodynamic forces, turbulence, shock waves, and cosmic feedback. By matching real observations with simulation outputs, scientists are able to test hypotheses about the nature of jet launch mechanisms, black hole spin, and accretion physics. The continued refinement of these simulations has led to increasingly accurate reproductions of lobe morphology and energy distribution. Double-lobed quasars are not merely exotic anomalies in the universe. They are key players in cosmic evolution. Their powerful jets inject energy into the intergalactic medium, redistribute matter across large volumes of space, and potentially influence the formation of new galaxies. In doing so, they help shape the large-scale structure of the universe itself. Some researchers argue that without such energetic outflows, galaxies might form too quickly and become too massive, throwing off the delicate balance needed for the formation of complex structures like stars, planets, and potentially life. From a more philosophical perspective, the sheer scale and persistence of these objects evoke a sense of cosmic wonder. Imagine a jet of particles fired millions of years ago, still carving its way through the void, illuminating space with its legacy of motion. These structures outlast their creators, and in a way, they serve as monuments to the processes that gave rise to them. In a universe defined by change and entropy, the lobes of a quasar stand as long-lived signatures of cosmic order emerging from chaos. One of the more speculative but exciting areas of research involves the connection between double-lobed quasars and dark matter or dark energy. While current models do not directly tie jet production to these mysterious components of the universe, some theories suggest that the large-scale distribution of dark matter might influence the direction and longevity of the jets. Additionally, studying the interaction between jets and cosmic voids might help probe the otherwise invisible scaffolding of dark matter that underpins the structure of the cosmos. Another emerging field of study is the use of machine learning to identify and classify double-lobed quasars in massive data sets. As sky surveys become more expansive and detailed, the sheer volume of data exceeds the capacity of human analysis. Machine learning algorithms trained on known examples can rapidly identify new double-lobed candidates, and even discover rare morphologies that might go unnoticed by traditional methods. This technological integration is accelerating discoveries and opening new avenues of inquiry at an unprecedented pace. The global astronomical community is also looking forward to the next generation of telescopes, particularly the James Webb Space Telescope, JWST, and the aforementioned Square Kilometre Array, SKA. These tools will provide unprecedented resolution and sensitivity, allowing scientists to peer deeper into the quasar's host galaxies, detect more distant jets, and explore the detailed mechanisms of energy transfer from black holes to lobes. The hope is that these instruments will not only confirm existing theories but uncover new physics that changes our understanding of black hole dynamics. Perhaps most compelling is the ongoing question: why do only some quasars develop double-lobed structures while others do not? Despite similarities in black hole mass and accretion rates, only a fraction of quasars display prominent radial lobes. The reason could lie in the black hole's spin, magnetic field configuration, environmental factors, or some combination of these elements. Unraveling this mystery could be the key to a unified theory of jet production and quasar evolution. These observations allow astronomers to trace how the jets propagate, how the energy is distributed within the lobes, and how this energy eventually disperses into the intergalactic medium. It's like watching the weather patterns of a galaxy, except these storms are made not of clouds and water, but of plasma, magnetic fields, and relativistic particles. The turbulent interactions within the lobes often leave behind complex filamentary structures, shock fronts, and cavities that can only be detected through careful analysis across multiple wavelengths. Each lobe becomes a time capsule of activity, recording the violent history of its central black hole. Additionally, lobes from double-lobed quasars provide a unique opportunity to map the intergalactic magnetic field, one of the least understood components of the cosmic web. As charged particles spiral along magnetic field lines, they emit synchrotron radiation, the strength and polarization of which reveals the geometry and intensity of the magnetic fields they encounter. By measuring this radiation across different portions of the lobes, astronomers can reconstruct a map of the intergalactic magnetic structure, like spraying paint into the air to see otherwise invisible wind patterns. Another important feature to note about double-lobed quasars is their spectral aging. As the particles in the lobes emit radiation over time, they lose energy, resulting in a predictable shift in the observed frequencies of the emitted light. This allows scientists to calculate how long the jets have been active, when they began, and even whether there have been multiple periods of jet activity. In some cases, researchers have discovered relic lobes, structures from an earlier jet episode that are now fading, located alongside fresh, newly active lobes. These relics hint at a repeating life cycle of quasar activity that may involve intermittent feeding of the central black hole. This possibility of multiple jet phases leads to an even more fascinating consideration. Some double-lobed quasars appear to have misaligned lobes, where the direction of newer jets differs slightly from older ones. This is often interpreted as evidence of black hole spin reorientation, possibly caused by galaxy mergers or accretion disk instabilities that torque the central black hole and change the direction of its axis. These dynamics reveal that supermassive black holes are not fixed entities, but dynamic engines whose orientations and outputs evolve based on their interactions with the surrounding cosmic environment. Indeed, mergers may be among the most significant contributors to the formation and evolution of double-lobed quasars. When two galaxies collide and their central black holes eventually coalesce, massive bursts of energy are unleashed. The merger injects vast amounts of gas into the core of the galaxy, potentially feeding the supermassive black hole and launching a new jet phase. Some of the most massive and powerful double-lobed quasars ever observed may have formed under exactly these conditions, making them cosmic signatures of ancient galactic collisions. The host galaxies of double-lobed quasars are often elliptical and massive, rich in old stars and low in gas content, conditions that are ideal for long-lived jet activity. These galaxies tend to reside in dense galactic environments like clusters, where external gas can be accreted to power the black hole over extended periods. In many cases, X-ray observations reveal large cavities in the surrounding hot gas, carved out by the pressure of the expanding radial lobes over time. These cavities are compelling evidence of the mechanical feedback process in action, where jets physically displace intergalactic matter across hundreds of thousands of light-years. Observations across the electromagnetic spectrum have become essential in constructing a full picture of double-lobed quasars. While radio observations reveal the jets and lobes, optical data from telescopes like Hubble help identify the host galaxies, and X-ray telescopes like Chandra detect the hot gas being disturbed by the jets. Infrared observations from instruments like the Spitzer or James Webb Space Telescopes help identify obscured regions of star formation and dust hidden behind the glare of the quasar. Gamma-ray telescopes, such as Fermi, are able to detect the most energetic emissions, which often trace the very base of the jets near the black hole itself. The combination of all these wavelengths, referred to as multi-wavelength astronomy, has transformed our understanding of quasars, especially the double-lobed kind. These cross-disciplinary observations allow scientists to piece together the life cycle of a quasar, from its birth in a gas-rich galaxy, through periods of intense jet activity, to its eventual decline as it runs out of fuel or is disrupted by environmental factors. What was once thought to be a singular object, bright and mysterious, is now understood as a dynamic process with distinct phases, feedback loops, and far-reaching consequences. It's also worth noting that not all jets form symmetrical lobes, and not all double-lobed structures are created equal. Some exhibit a clear brightness disparity between one lobe and the other, a phenomenon known as jet-sidedness. This is often attributed to relativistic beaming, where one jet is pointed more directly toward Earth, making it appear brighter due to the Doppler boosting of light traveling close to the speed of light. This effect gives us critical information about the angle at which we are observing the quasar and helps astronomers refine models of jet speed and orientation. In rarer cases, we encounter X-shaped radio quasars, where the lobes appear to form an X pattern instead of a simple double line. These may represent cases where the jet direction has dramatically shifted over time, possibly due to a merger or gravitational torque that reoriented the black hole. The older, fading lobes remain visible, crisscrossing with the newer ones, giving the appearance of an X. These sources challenge traditional models of jet mechanics and offer additional insights into how flexible and reactive the central engine of a quasar can be. Even more unusual are quasars with triple or multiple lobes, which may result from episodes of interrupted jet activity or precessing jets that carve out corkscrew patterns through space. These complex configurations are difficult to model but provide rich data for simulations that attempt to mimic real cosmic behavior. The more we observe these anomalies, the more we realize just how versatile and multifaceted quasar engines truly are. Understanding double-lobed quasars also contributes to solving one of the greatest mysteries in modern cosmology: the nature of dark matter and dark energy. Because these quasars often sit at the centers of galaxy clusters, their jets and lobes interact with the dark matter halos that hold these clusters together. Mapping how the lobes move, bend, and evolve can help scientists infer the distribution and behavior of invisible mass around them. Similarly, their role in regulating star formation and galactic feedback processes plays into larger questions about the universe's energy balance over time. Moreover, double-lobed quasars act as cosmic beacons, visible from across the universe. Their jets and lobes stretch so far that they can serve as tools for measuring cosmic distances, tracking the expansion of space, and mapping the large-scale structure of the cosmos. As natural probes, they allow us to study otherwise unreachable regions of intergalactic space, revealing the cosmic web of matter and energy that binds everything together. By comparing the spectral signatures of old and new lobes, scientists can determine the timescales over which quasars cycle through active and dormant phases. These patterns suggest that supermassive black holes don't simply power jets continuously for billions of years, but rather operate in bursts, alternating between intense outflows and quieter periods where little or no jet activity occurs. This behavior could be regulated by the availability of infalling material, changes in accretion disk structure, or even the gravitational influence of nearby galaxies. Understanding these cycles adds depth to our models of black hole evolution and their broader role in galactic ecosystems. The feedback effect of these jets on their surroundings is another area of growing research. As double-lobed quasars inject massive amounts of energy into the surrounding interstellar and intergalactic medium, they can profoundly influence star formation rates, galaxy evolution, and the distribution of cosmic gas. This feedback can suppress or even quench star formation by heating gas to the point where it no longer cools and collapses into stars, a phenomenon known as quasar mode feedback. In this way, double-lobed quasars may act as both creators and destroyers, fostering galaxy growth while also imposing strict limits on it. Yet, the story of double-lobed quasars is not limited to their large-scale effects. The microphysics of jet formation, how exactly matter and magnetic fields interact near the event horizon of a black hole, remains one of the most tantalizing mysteries in astrophysics. Simulations show that twisted magnetic field lines near rapidly spinning black holes can extract rotational energy, a process described by the Blandford's-Najek mechanism. This process is thought to be a key driver behind the powerful jets of radio-loud quasars. However, direct observational confirmation remains elusive, and only with continued technological advances in high-resolution imaging and multi-wavelength astronomy can we hope to unlock these secrets. On a cosmological scale, double-lobed quasars serve as probes of the distant universe. Their immense brightness and structural complexity make them ideal candidates for gravitational lensing studies, where their light is bent by intervening mass. Such lensing not only magnifies the quasar, revealing fine structural detail, but also provides information about the distribution of dark matter in the foreground galaxy or cluster. Some double-lobed quasars have even been used to test the constancy of physical laws over time, such as the fine structure constant, offering a rare opportunity to check if the laws of physics have changed across billions of years. Moreover, double-lobed quasars give us a window into the formation of large-scale structure in the universe. Their alignment with cosmic filaments and voids offers clues about the gravitational landscape of the cosmos. In many cases, jets from double-lobed quasars appear to follow the orientation of nearby cosmic filaments, suggesting that the structure of the universe at large influences the behavior of individual galaxies. This reinforces the notion that nothing in the universe exists in isolation. Everything is shaped by the complex, dynamic web of matter and energy stretching across space-time. Interestingly, not all double-lobed quasars are symmetrical. Some show a pronounced asymmetry, with one lobe significantly longer, brighter, or differently shaped than the other. This asymmetry can be caused by a number of factors: differences in the density of the intergalactic medium on either side of the host galaxy, relativistic beaming effects where one jet is pointed more directly toward Earth, or even past interactions with other galaxies or large gas clouds. These imbalances tell a story, each one unique, and offer clues about the hidden properties of the environments these jets pass through. Another fascinating phenomenon tied to double-lobed quasars is the presence of hotspots, bright regions at the tips of the jets where the outflowing particles collide violently with the surrounding medium. These hotspots are where the energy of the jets is finally dissipated and converted into radiation, producing intense synchrotron emissions that can be detected across radio, optical, and even X-ray wavelengths. Hotspots are transient, moving slightly as the jet wiggles or encounters resistance, and their motion over time has been mapped in some systems to calculate the velocity and direction of the jets with remarkable precision. Further back from the hotspots are the cocoon regions, where the jets have inflated vast bubbles of relativistic plasma. These cocoons envelop the jets and expand laterally as well as longitudinally, creating pressure fronts that reshape the surrounding gas. The interaction between the cocoon and the ambient medium can generate secondary shock waves and even trigger star formation in previously dormant gas clouds. In this way, double-lobed quasars don't merely disrupt, they sometimes ignite new cosmic activity in their wake. The evolution of double-lobed quasars over cosmic time is an active field of study. Older lobes, especially those in the process of fading, provide insight into how quasars die. As the central engine slows and eventually stops producing jets, the lobes begin to cool and lose brightness. Their radio emissions shift to lower frequencies, and they become more difficult to detect. Some are only found in low-frequency surveys, where their extended, ghostly forms can still be seen haunting the void. These remnants, called radio relics or radio ghosts, may be re-energized by future events, such as new jet activity or the passage of shock waves from galaxy mergers. In the realm of classification, astronomers have devised various systems to categorize double-lobed quasars and related radio sources. One of the most prominent is the Fanaroff-Riley classification, which divides radio galaxies and quasars into two types: FRI, where the brightness decreases along the jet, and FR2, where the hotspots at the lobe ends are brightest. Most double-lobed quasars fall into the FR2 category, characterized by highly collimated, powerful jets and prominent terminal hotspots. This classification helps researchers understand the relationship between jet power, environment, and morphology. With the upcoming generation of telescopes, the study of double-lobed quasars is poised to enter a new era. Instruments like the James Webb Space Telescope, JWST, the Extremely Large Telescope, ELT, and especially the Square Kilometre Array, SKA, will provide unprecedented resolution and sensitivity. These tools will allow astronomers to detect fainter lobes, probe deeper into their structure, and even observe their formation in real time in nearby active galaxies. Combined with advanced simulations, we may soon reach a point where we can predict the life cycle of a quasar based on its initial conditions. Perhaps the most exciting prospect lies in the potential for multi-messenger astronomy, the combination of data from light, gravitational waves, neutrinos, and cosmic rays. If a double-lobed quasar is associated with events like black hole mergers or neutrino bursts, we could gain a holistic picture of the processes occurring deep within these powerful engines. Coordinated observations across the electromagnetic spectrum and beyond could finally unlock the deepest secrets of jet formation, black hole spin, and energy extraction on cosmic scales. As we look further into the study of double-lobed quasars, one of the most exciting possibilities is the potential discovery of new types of outflows. While we've become familiar with the standard image of a quasar emitting powerful jets in two directions, the discovery of alternative jet configurations, such as triple or quadruple lobes, could expand our understanding of black hole feedback. These outflows may form when more complex gravitational interactions are at play, such as the interaction of two supermassive black holes within the same galaxy, or the influence of large-scale cosmic filaments that help direct jet activity in more intricate ways. In some cases, the orientation of a quasar's jets is not as simple as pointing outward from the center. Double-lobed quasars can exhibit jet precession, where the direction of the jets shifts over time. This precession could be due to the gravitational influence of nearby objects, such as a companion galaxy or a close stellar object that disturbs the black hole's spin axis. This phenomenon can lead to a wobbling of the jet orientation, creating a shifting, dynamic system of lobes that changes on timescales ranging from thousands to millions of years. Interestingly, the presence of such a wobbling effect may be key to understanding the multiphase structure of the material surrounding quasars. A single quasar jet may be interacting with a variety of media, ranging from the cold, dense clouds of gas near the galaxy to the hot, diffuse plasma far from the central engine. By studying how these materials respond to the changing dynamics of the jet, we can begin to comprehend how large-scale galactic ecosystems evolve. In particular, the study of gas flows within the lobes could provide insights into the transition from a gas-dominated phase to one where stars begin to form, bridging the gap between quasars and their eventual decline into more typical galaxies. One of the most profound consequences of double-lobed quasars is their role in the cosmic feedback loop. The energy released by quasar jets and their associated shockwaves acts as a regulator for star formation within their host galaxies. This feedback mechanism is a fundamental process for understanding the growth of galaxies over cosmic time. In galaxies where the quasar activity is intense, the energy expelled by the jets can prevent gas from cooling and collapsing into stars, effectively suppressing star formation. Conversely, in galaxies where quasar activity wanes, the gas can begin to cool, collapse, and trigger a new phase of star formation. The study of this feedback is crucial for explaining why galaxies like our own Milky Way are currently in a more dormant state, with star formation rates significantly lower than in their earlier years. It's thought that quasars and their intense jets were more prevalent in the early universe, playing a major role in shaping the galaxy population we observe today. This feedback not only affects individual galaxies but may also have far-reaching consequences on the overall evolution of large-scale cosmic structures. By regulating the flow of gas between galaxies and clusters, quasars may help shape the architecture of the universe itself, influencing the formation of cosmic voids, filaments, and clusters. What makes double-lobed quasars particularly valuable for the study of galactic evolution is their visibility across vast distances. These powerful objects can be observed at redshifts so high that we are looking back in time billions of years to a period when the universe was much younger. Because quasars are typically powered by supermassive black holes that formed early in the universe's history, studying them offers a window into the conditions that prevailed in the early universe. As a result, double-lobed quasars can serve as cosmic time capsules, providing clues about how galaxies and black holes co-evolved during the formative stages of the cosmos. Moreover, quasars like these provide critical evidence for understanding the relationship between black holes and their host galaxies. As massive black holes grow, they can influence the dynamics of the surrounding gas, often seen in the alignment of quasar jets with the host galaxy's major axis. Some researchers hypothesize that the jets themselves may play a role in aligning the galaxy's overall structure, influencing everything from the distribution of stars to the morphology of the galaxy's spiral arms. This process of alignment may represent an important piece of the puzzle in understanding how the growth of black holes and galaxies are intertwined over time. The interaction between multiple quasars within galaxy clusters or groups is another key area of interest. Many quasars are not isolated but are instead part of larger structures, and their jets can intersect, overlap, or even interact with the outflows from other black holes in the same region. This can create a highly dynamic and complex environment, with multiple sources of energy feeding into the intergalactic medium. In some cases, the collision of jets can lead to the formation of unusual phenomena, such as shock fronts or even complex radio structures that don't easily fit into the standard models of quasar activity. As more observational data becomes available, astronomers are also discovering that the black hole mass-luminosity relationship plays a crucial role in determining the size and power of quasar jets. More massive black holes tend to produce stronger, more extended jets, which in turn can result in larger, more prominent double-lobed structures. This relationship opens up a new avenue of research, where scientists are working to determine how the growth of black holes influences not just their immediate surroundings, but the entire galaxy. By studying the size and shape of quasar jets, astronomers can infer the mass of the black hole and learn more about its evolutionary history. Another aspect of double-lobed quasars that's gaining attention is their connection to galaxy mergers. Many of the most powerful quasars are found in regions where galaxies are undergoing interactions or mergers. These cosmic collisions may trigger the infall of gas and dust into the supermassive black holes at the galaxy's centers, leading to an increase in quasar activity. Furthermore, the gravitational disturbances caused by the merger could induce changes in the orientation or shape of the jets, leading to more complex, non-symmetric double-lobed structures. In this way, double-lobed quasars may act as a tracer of galaxy merger history, helping us to better understand the processes that drive galaxy growth and evolution. Despite the wealth of data available on quasars, one of the biggest challenges remains the lack of precise models for the behavior of these extraordinary systems. While we have detailed numerical simulations of black hole accretion and jet formation, the actual physical conditions within a quasar's vicinity remain poorly constrained. Key questions, such as the precise mechanism that causes jets to accelerate to relativistic speeds, or the exact role of magnetic fields in shaping jet dynamics, continue to be a topic of intense debate. As observational techniques improve and theoretical models become more sophisticated, we can expect significant progress in answering these fundamental questions. In the future, advances in technology and observation techniques will provide even greater insight into the world of double-lobed quasars. The next generation of radio telescopes, such as the Square Kilometre Array (SK) and the Very Large Telescope (VLT), will offer an unprecedented ability to observe these objects in greater detail. These instruments will enable us to probe the internal structure of quasars, track the movement of jets over time, and even detect faint, distant double-lobed quasars at higher redshifts. Such observations will help to push our understanding of these enigmatic objects to new heights. With these advancements in observational technology, scientists will also have the opportunity to delve into the polarization of quasar jets, a critical tool in understanding their physical properties. Polarization occurs when electromagnetic waves, such as light, are oriented in a specific direction, and studying this phenomenon in quasar jets could reveal much about their magnetic fields. These magnetic fields are essential in guiding the plasma within the jets, potentially shaping the morphology of the lobes. By measuring the polarization of light emitted by the jets, researchers can gain a more precise understanding of the jet's orientation, its composition, and even the processes that power the quasar itself. One of the most exciting developments in quasar research is the rise of multi-messenger astronomy, which combines observations from different types of electromagnetic radiation, such as optical, radio, infrared, and X-rays, with observations from gravitational waves and neutrinos. Double-lobed quasars, being highly energetic sources, are prime candidates for this type of multifaceted study. By observing quasars across the electromagnetic spectrum, scientists can build a much more comprehensive picture of their behavior, while simultaneously using gravitational wave detectors to study the effects of interactions between supermassive black holes. This interdisciplinary approach is poised to yield breakthroughs in our understanding of how black holes form, grow, and interact with their environments. Moreover, the advent of machine learning and artificial intelligence is likely to revolutionize the way scientists analyze data from quasars. With massive amounts of observational data pouring in from telescopes around the world, manual analysis can be slow and cumbersome. Machine learning algorithms can sift through this data much more efficiently, identifying patterns and correlations that would be difficult, if not impossible, for humans to detect. These algorithms can assist in identifying new double-lobed quasars in vast datasets, analyzing the intricate dynamics of quasar jets, and even helping to refine the models that describe quasar formation and evolution. A particularly fascinating aspect of studying double-lobed quasars lies in the potential for these objects to reveal hidden aspects of the cosmic expansion. The light emitted by quasars, which travels across billions of light-years, serves as a sort of cosmic time capsule that carries information about the universe's past. By studying the light curves and emission spectra of these distant quasars, astronomers can measure how the expansion of the universe has affected the properties of galaxies and quasars over time. These observations provide a unique glimpse into how the universe has evolved, from the first moments after the Big Bang to the present day, and could lead to deeper insights into the very fabric of space-time. Furthermore, double-lobed quasars could help resolve some of the most intriguing questions about dark matter and dark energy. These mysterious substances account for the vast majority of the universe's mass and energy, yet they remain poorly understood. Some researchers propose that studying the behavior of quasar jets could provide indirect evidence of dark matter's influence, particularly in how it might affect the motion of gas around black holes. By examining how the jets of quasars interact with surrounding galaxies and the large-scale structure of the universe, scientists may be able to uncover hidden signatures of dark matter that would otherwise remain undetectable. The role of double-lobed quasars in the broader context of cosmology is also incredibly important. The jets emanating from these quasars play a significant part in regulating the intergalactic medium, IGM. The high-energy radiation and particle flows from quasars can heat and ionize the gas in the intergalactic space, altering its composition and density. This process of heating and ionization has profound effects on the formation of galaxies, as it influences how gas cools and condenses to form stars. Quasars essentially act as cosmic engines, driving the evolution of the universe by shaping the conditions under which stars and galaxies form. In addition, the study of quasar jets can also provide important clues about the fate of supermassive black holes over cosmic time. There is still much debate about whether these black holes continue to grow indefinitely or whether they eventually cease their activity and become dormant. Double-lobed quasars are one of the most promising areas of research for answering this question. The feedback processes that quasar jets initiate in their host galaxies may play a crucial role in determining whether the black holes continue to accrete matter or whether they exhaust their fuel and fade away into quiet, non-active states. This is an essential piece of the puzzle in understanding the long-term evolution of black holes and their influence on the galaxies they inhabit. Interestingly, some studies have also proposed that the behavior of quasar jets could be influenced by the presence of a companion black hole. In cases where a double-lobed quasar is in a galaxy merger, two supermassive black holes could potentially orbit each other, leading to complex jet interactions. These interactions might cause the jets to become misaligned or precess, further complicating the structure of the lobes. The discovery of binary supermassive black holes in such systems could provide valuable insights into how these interactions affect the energy output and morphology of the quasars they power. Another avenue of research is the connection between double-lobed quasars and active galactic nuclei, AGN. While quasars are often associated with the most energetic forms of AGN, they represent just one part of the AGN family. AGN come in many forms, from Seyfert galaxies to radio galaxies, and the study of double-lobed quasars helps to bridge the gap between these different types of active galaxies. By comparing the characteristics of double-lobed quasars with other AGN, scientists can begin to understand the full range of behaviors that these extraordinary objects exhibit. Moreover, quasars themselves can vary significantly in terms of their luminosity, jet orientation, and the presence of certain spectral features, making them an excellent laboratory for studying the diversity of AGN. Ultimately, double-lobed quasars represent a gateway to understanding some of the most fundamental questions about the universe. As we continue to probe deeper into the cosmic landscape, these enigmatic objects will undoubtedly reveal more of their secrets. Through advanced technologies, interdisciplinary collaborations, and innovative research methods, scientists will continue to unlock the mysteries of quasars and their impact on the evolution of galaxies, black holes, and the universe as a whole. In the grand scheme of things, studying double-lobed quasars is not just about observing individual objects, but is a key piece of the larger cosmic puzzle that spans across billions of years and stretches to the very edges of our understanding of the universe. As we look to the future, the role of next-generation telescopes in the study of double-lobed quasars cannot be overstated. The upcoming James Webb Space Telescope, JWST, along with the Square Kilometre Array, SK, and other ground-based observatories, will offer unprecedented capabilities to observe quasars across a broader spectrum and with higher resolution. These new telescopes will enable astronomers to gather more detailed images and spectra of distant quasars, allowing for a deeper understanding of how the jets interact with their surrounding environments. The ability to observe these objects in multiple wavelengths, from radio waves to infrared to visible light, will allow scientists to map out the structure of double-lobed quasars in ways that were once unimaginable. By using the infrared capabilities of the JWST, for instance, astronomers will be able to peer through the dust and gas clouds that often obscure our view of the innermost regions of quasars. This will provide a clearer picture of the central supermassive black hole and the surrounding accretion disk, offering critical insights into the processes that drive the production of powerful jets. Additionally, the next generation of telescopes will be able to observe quasars at greater distances than ever before. Some of these distant quasars were likely formed in the early universe, when galaxies and black holes were still in the process of formation. By studying double-lobed quasars that date back to these early epochs, scientists can gain insights into how black holes grew, evolved, and affected the development of galaxies during the cosmic dawn. This research will help us understand the nature of the universe during its infancy and the critical role played by quasars in shaping the cosmos. As quasar jets interact with the intergalactic medium, IGM, they also play a role in shaping the large-scale structure of the universe. The high-energy particles emitted by the jets can influence the surrounding gas clouds and even affect the formation of galaxy clusters. The feedback processes driven by quasars may also be responsible for preventing certain regions of space from collapsing into new galaxies, by dispersing the gas and heating it to such an extent that star formation is halted. This type of galactic feedback helps regulate the number of stars and galaxies that form within a given region of the universe. Some researchers have even suggested that the energetic outflows from quasars, including those of double-lobed quasars, may be responsible for a cosmic thermostat effect. This concept posits that quasars act as regulators of the temperature and density of the IGM, ensuring that the gas does not become too dense and collapse to form excessive numbers of stars. In this sense, quasars serve as cosmic gatekeepers, ensuring that the universe remains in a delicate balance, preventing runaway star formation that could lead to an unstable, overly energetic cosmos. The energy released by these outflows also has profound implications for the cosmic ionization history. As quasars emit high-energy radiation, they can ionize the surrounding hydrogen gas, creating a bubble of ionized material around the quasar. This process played a significant role during the epoch of reionization, a period in the early universe when the first stars and galaxies began to ionize the neutral hydrogen that permeated the universe. The study of double-lobed quasars, which emit intense radiation and particles, provides a window into this important period of cosmic history, allowing scientists to better understand how the universe transitioned from a dark, neutral state to the ionized, transparent universe we observe today. At the heart of all these discoveries is the supermassive black hole, whose mysterious nature continues to puzzle scientists. Double-lobed quasars are particularly fascinating in this regard because their energy output is often thought to be directly linked to the accretion disk of material that surrounds the black hole. The way this material is funneled into the black hole, the formation of the relativistic jets, and the precise mechanisms by which the energy is emitted are still not fully understood. New theoretical models and simulations are constantly being developed to explain these processes, and with the help of advanced observational tools, astronomers hope to finally crack the code. In recent years, the study of quasars has become increasingly interconnected with theoretical physics. Many of the properties of quasar jets challenge our current understanding of high-energy astrophysics, particularly in terms of how matter behaves under extreme conditions. The forces at play near a supermassive black hole are so intense that they push the boundaries of what we know about physics, especially in the realms of general relativity and quantum mechanics. Understanding how these forces work together to produce the jets that shape double-lobed quasars could provide key insights into fundamental physics and lead to a deeper understanding of the universe's laws. The study of double-lobed quasars also ties into the larger search for extraterrestrial intelligence, ETI. While quasars are not directly related to the search for alien life, the search for unusual signals in the radio waves emitted by quasars could provide a new avenue for SETI researchers. The intense energy and broad frequency range of quasar emissions make them an interesting subject for analysis in the search for artificial signals. By studying the signals that come from quasars, scientists can gain more insight into how to distinguish between natural astrophysical sources and potentially artificial transmissions. Moreover, quasar research intersects with questions about the origin of life in the universe. The extreme conditions near supermassive black holes, such as those in double-lobed quasars, may seem inhospitable to life as we know it. However, these environments also serve as natural laboratories for studying the kinds of chemistry and physics that could have led to the formation of life on Earth. The energetic processes in these regions may have contributed to the synthesis of complex molecules or provided the necessary conditions for the formation of habitable environments elsewhere in the universe. With the continued progress in quasar research, astronomers are beginning to make more accurate predictions about the future behavior of quasars. As we observe these objects in the present day, we are essentially looking into the past. The light we see now was emitted billions of years ago, so understanding the current state of quasars helps us learn about their earlier histories. With future observations, especially those made through more advanced telescopes and instruments, scientists will be able to refine their models of quasar evolution, shedding light on what the future holds for these mysterious objects and the black holes that power them. Double-lobed quasars remain one of the most fascinating and enigmatic phenomena in the universe. Their immense energy output, complex structures, and potential links to the formation and evolution of galaxies make them key players in the ongoing quest to understand the cosmos. With the help of cutting-edge technology and innovative research, astronomers are poised to uncover new insights into the behavior of these objects and the mechanisms that drive their powerful jets. As our knowledge deepens, double-lobed quasars will continue to be a source of inspiration, unlocking the mysteries of the universe and expanding our understanding of the forces that govern everything around us. As we continue to explore the profound nature of double-lobed quasars, it's important to emphasize how they fit into the broader narrative of cosmic evolution. These objects serve as more than just intriguing anomalies. They are a key element in understanding the larger processes that shape galaxies and their interactions with the surrounding universe. One fascinating aspect of double-lobed quasars is how they help illuminate the relationship between black holes and galaxies. It's widely accepted that most galaxies, including our own Milky Way, harbor a supermassive black hole at their centers. In some cases, these black holes are relatively dormant, exerting little influence on their surroundings. However, in active galactic nuclei, AGN, including those powered by double-lobed quasars, the supermassive black hole is actively consuming material, generating immense radiation in the process. This active consumption of material is central to our understanding of galaxy formation and growth. The powerful outflows and jets produced by quasars can influence the galaxy's structure, heating and expelling gas, which in turn regulates star formation. This process is known as AGN feedback, and it's thought to play a crucial role in preventing galaxies from becoming too large or too bright. Quasars, by regulating the gas supply available for star formation, may be preventing galaxies from overgrowing in size and luminosity. Thus, double-lobed quasars are not just active black holes, they are also cosmic regulators that influence the evolution of their host galaxies. Moreover, these cosmic feedback processes are critical in understanding the environmental effects of quasars. While we traditionally think of quasars as distant, isolated phenomena, their jets and radiation have the power to affect their surrounding environments on a large scale. As the jets travel through intergalactic space, they interact with the surrounding gas and dust, injecting energy into the intergalactic medium, IGM. This interaction can cause the gas to heat up, alter its density, and even expel it from the galaxy entirely. Such feedback mechanisms contribute to the large-scale structure of the universe, influencing the formation of galaxy clusters and other cosmic structures. The study of double-lobed quasars also has implications for cosmology, particularly when it comes to understanding the large-scale distribution of matter in the universe. By analyzing how the jets of these quasars affect the surrounding medium, scientists are able to map out the distribution of gas, dark matter, and other materials across vast distances. These observations help create a more detailed and accurate picture of the large-scale structure of the universe, which is essential for understanding its evolution over billions of years. It's also worth considering the cosmic distance to quasars and how this affects our observations. Given their immense energy output, quasars are often visible from great distances, sometimes billions of light-years away. This means that when we observe a double-lobed quasar, we're not just looking at the present state of that object, we are looking back in time. The light we see today was emitted millions or even billions of years ago, providing us with a snapshot of the universe at an earlier stage in its evolution. This time lag provides astronomers with a unique opportunity to study the universe as it was in the distant past, allowing for comparisons between the conditions that existed long ago and what we see in the present day. In addition to their importance in cosmic history, double-lobed quasars are also key to understanding the fundamental physics of the universe. As already mentioned, the extreme conditions near a supermassive black hole push the boundaries of what we know about physics. The behavior of matter and energy in these environments tests our understanding of general relativity, quantum mechanics, and other fundamental theories. For example, the jets of these quasars travel at nearly the speed of light, and their relativistic speeds result in strange and often counterintuitive phenomena, such as time dilation and the bending of light. These effects challenge our traditional understanding of how the laws of physics apply under such extreme conditions, and they may offer clues to unresolved questions in theoretical physics. Moreover, the study of double-lobed quasars helps bridge the gap between observational astrophysics and theoretical models. In the past, astronomers were limited to studying quasars and other celestial objects purely through observation, gathering data from telescopes and interpreting it within the framework of existing theories. Today, however, theoretical physicists and astronomers work hand-in-hand to develop models that can explain the extreme phenomena associated with quasars, from their jets to the behavior of their central black holes. These models are continuously refined based on new observations, leading to a more accurate and comprehensive understanding of the universe's most energetic objects. One particularly intriguing aspect of double-lobed quasars is the question of why they emit jets at all. It's well established that these quasars have relativistic jets, but the mechanisms that produce these jets remain a subject of active research. The most widely accepted model suggests that the jets are generated by the accretion disk surrounding the supermassive black hole. As material from the surrounding galaxy falls into the black hole, it heats up and forms an accretion disk. The intense gravitational and magnetic fields in this region generate powerful outflows, which eventually form the jets observed in double-lobed quasars. Yet, the precise details of this process are still not fully understood. For example, while we know that magnetic fields play a crucial role in the formation of jets, the exact nature of these fields, how they are generated, how they interact with the accretion disk, and how they influence the direction and shape of the jets, remains a topic of much debate. Additionally, while jets are typically aligned with the spin axis of the black hole, not all jets follow this alignment perfectly, suggesting that other factors, such as the surrounding gas environment or the orientation of the galaxy, may also influence their behavior. In recent years, computer simulations have become an invaluable tool in understanding the complex processes that govern quasar jets. These simulations model the behavior of matter, radiation, and magnetic fields around supermassive black holes, allowing scientists to explore different scenarios and test the validity of various theoretical models. By comparing the results of these simulations with real observational data, researchers are gaining new insights into the mechanisms behind jet formation and the factors that shape the appearance of double-lobed quasars. Furthermore, the interaction between the jets and the surrounding environment raises important questions about the longevity and stability of quasar jets. Some of these jets are incredibly stable, lasting millions or even billions of years, while others appear to be more transient, flickering on and off over time. Understanding the factors that govern the lifespan and stability of these jets is a key challenge in quasar research. It's possible that the availability of material in the accretion disk, the strength of the black hole's magnetic field, or the density of the surrounding gas all play a role in determining how long a quasar's jets will remain active. Double-lobed quasars are not just interesting because of their extreme energy output or their connection to galaxy formation. They also represent one of the most significant astrophysical phenomena in terms of their potential to unlock new knowledge about the universe. Whether through the study of their jets, their feedback effects on galaxies, or the ways in which they challenge our understanding of fundamental physics, these objects continue to be a central focus for astronomers and physicists alike. Their complex nature serves as a reminder that we are still only scratching the surface when it comes to understanding the true dynamics of the cosmos. As technology advances, and as we push the boundaries of what we can observe, the mysteries of double-lobed quasars will continue to captivate us and propel us toward deeper discoveries in the field of astrophysics. As we continue to explore the nature of double-lobed quasars, one key aspect that becomes evident is their connection to the larger-scale cosmic evolution and their role in shaping the structure of the universe. These quasars, with their immense energy output and far-reaching influence, offer a window into the formative processes that have shaped galaxies, clusters, and the vast cosmic web of interconnected matter and energy we observe today. Quasars, including double-lobed quasars, are considered cosmic beacons, emitting more energy than entire galaxies, making them visible across billions of light years. Because of this, they allow us to peer into the past of the universe, effectively offering snapshots of what the cosmos looked like when it was much younger. These objects give us a unique way to probe the properties of distant galaxies and study how active galactic nuclei have evolved over time. By observing how quasars affect the regions around them, we can learn not only about their direct environment, but also about the conditions that existed in the universe at different epochs. One particularly intriguing aspect of these distant observations is their ability to shed light on the nature of early galaxies. The energy emitted by quasars can affect the surrounding intergalactic medium, heating and ionizing the gas that exists between galaxies. This process can alter the structure of the IGM, shaping how matter is distributed across the universe. In the early universe, quasars were more abundant, and their influence was likely more profound. By studying the feedback mechanisms associated with double-lobed quasars, scientists can better understand the role these objects played in shaping the early universe's structure. In terms of the cosmic distance ladder, double-lobed quasars are incredibly useful. Their immense luminosity makes them one of the brightest objects in the universe, allowing astronomers to measure their distances with relatively high precision. By examining the redshift of their emitted light, how much it has stretched as the universe has expanded, we can calculate the distance to these objects and use them as cosmological probes. This ability to measure vast distances has significant implications for our understanding of the size, age, and expansion rate of the universe, helping to refine our models of cosmology and the underlying structure of the cosmos. As we look closer at the specific features of double-lobed quasars, their jet dynamics are of particular interest. These jets, often ejected at nearly the speed of light, exhibit several key characteristics that make them both fascinating and difficult to fully comprehend. For one, their relativistic speeds mean that they are subject to extreme time dilation effects. To an observer outside the quasar system, the jet may appear to travel slower than it actually is, a result of the relativistic velocities at play. Furthermore, the directionality of the jets can be influenced by several factors, including the alignment of the accretion disk, the orientation of the black hole's spin axis, and the properties of the surrounding gas and magnetic fields. These factors can lead to different kinds of interactions between the jets and the galaxy, including shock waves that further heat and energize the surrounding environment. In addition to these structural complexities, the composition of the jets themselves remains an area of ongoing study. Quasar jets are primarily composed of ionized gas, including electrons, protons, and various heavier elements, but the exact mixture can vary depending on the conditions near the black hole. As the jet material travels outward, it can collide with surrounding gas, forming shock fronts and synchrotron radiation, which produce the distinctive radio emissions associated with many double-lobed quasars. These high-energy emissions offer a powerful tool for astronomers to study not just the jets themselves, but the larger physical environment of the quasar. Interestingly, not all double-lobed quasars display identical characteristics, and this diversity is part of what makes them so interesting to researchers. While the double-lobed structure, with jets emanating from opposite sides of the black hole, is a defining feature, the jets themselves can exhibit a wide range of shapes and sizes, depending on a number of factors. Some jets may be symmetrical, while others may exhibit asymmetry, with one lobe being significantly brighter or more energetic than the other. In some cases, the jets can even appear to be misaligned, indicating that the quasar's black hole may be oriented at an angle relative to the plane of the galaxy. These variations suggest that there may be more than one process at work in shaping the behavior of quasars, and further studies will be needed to determine what factors control these differences. The magnetic fields around double-lobed quasars are another area of intense interest. Magnetic fields are thought to play a crucial role in the formation and collimation of jets, guiding the outflows from the accretion disk and helping to shape the jet's trajectories. Understanding how these magnetic fields are generated, and how they interact with the material in the accretion disk, is a key area of research. Some scientists hypothesize that the magnetic fields in quasar jets could be related to the presence of a rotating black hole, whose spin generates powerful magnetic fields through the Blandford's-Nagic mechanism, which could help launch the jets outward. Others believe that magnetic fields may arise from dynamo processes in the accretion disk, where the motion of charged particles generates the fields that ultimately power the jets. As we look toward the future of quasar research, observational advancements will play a critical role in advancing our understanding of double-lobed quasars. The development of next-generation telescopes and instruments, including the James Webb Space Telescope and the Square Kilometre Array (SKA), will allow for more detailed and higher-resolution observations of these objects. These instruments are capable of observing a wide range of wavelengths, from radio to infrared to X-rays, which will provide a more comprehensive picture of how quasars function. In particular, the SKA promises to greatly enhance our understanding of radio jets, enabling researchers to study the fine details of the jet's behavior and their interactions with the intergalactic medium. In addition to these telescopic advancements, theoretical models will continue to evolve as researchers work to explain the various phenomena associated with double-lobed quasars. By combining data from both observation and simulation, scientists can develop more accurate models of quasar jet formation, black hole accretion processes, and the feedback effects these quasars have on their surrounding galaxies. As our theoretical understanding deepens, we will likely uncover even more mysteries about the role of double-lobed quasars in shaping the structure and evolution of the universe. Ultimately, the study of double-lobed quasars represents a convergence of several important fields in astronomy, from black hole physics to galaxy evolution to cosmology. By studying these extreme objects, we not only learn about the most energetic processes in the universe but also gain insight into the underlying mechanisms that govern the evolution of galaxies, stars, and the cosmos as a whole. As we continue to unravel the mysteries of double-lobed quasars, we take another step toward understanding the vast, complex, and awe-inspiring universe in which we live. Double-lobed quasars are not just fascinating objects to study because of their dramatic structures and energy output. They also provide essential clues about the mysteries of black holes. These active galactic nuclei, where supermassive black holes reside, are among the most extreme and energetic environments in the universe. The material surrounding these black holes, in the form of the accretion disk, is subjected to intense gravitational forces, causing it to heat up to millions of degrees, emitting powerful X-rays and ultraviolet radiation. These processes are critical to understanding how black holes grow and how they influence their galaxies. The fascinating thing about double-lobed quasars is the feedback loop they create. The powerful jets that emanate from these supermassive black holes do more than just shoot out material into space. They play a crucial role in regulating the growth of galaxies themselves. These jets can carry energy into the surrounding environment, heating the gas and preventing it from cooling down enough to form new stars. This interaction between the black hole, its accretion disk, and the surrounding gas creates a feedback mechanism that can either stimulate or suppress star formation within the host galaxy. This process is critical to the evolution of galaxies and how they develop over cosmic time. Another critical area where double-lobed quasars provide insight is the central black hole's role in galaxy formation. The gravitational forces at play near the event horizon, the boundary beyond which not even light can escape, are so immense that they shape the surrounding space-time fabric itself. These forces give rise to phenomena such as gravitational lensing, where the light from distant objects is bent as it passes near the black hole. This lensing effect allows astronomers to observe galaxies and other objects that would otherwise be too distant or faint to detect. By studying how light bends around these massive black holes, scientists gain further understanding of their mass, size, and the complex relationship between black holes and galaxies. While double-lobed quasars provide a window into the extreme nature of the universe, they also raise several important questions. One key question is how quasars and their jets evolve over time. Are all quasars born with this characteristic double-lobed structure? Or is it the result of specific conditions, such as the alignment of the black hole's spin axis relative to the host galaxy? Researchers continue to debate whether double-lobed quasars represent an early stage of a quasar's life cycle, or if they are simply one of many types of quasar configurations. This remains an open question in astrophysical research, and will likely be answered through the continued development of simulations and observations across different wavelengths. It's also important to note that environmental factors play a crucial role in shaping the final appearance and behavior of quasars. For instance, the density of gas in the surrounding galaxy, and the availability of material for the accretion disk can heavily influence the intensity of the jets. A quasar embedded in a rich, gas-rich galaxy may have more material available to fuel its black hole, potentially leading to more powerful outflows. Conversely, a quasar located in a lower-density region may exhibit a less active accretion process, with weaker jets or even the absence of them. The relationship between the galaxy and its central black hole is complex, and the characteristics of the jets emanating from double-lobed quasars are a direct consequence of this relationship. Another important facet to consider is the impact of these quasars on their host galaxies. The powerful jets can disrupt the interstellar medium of the galaxy, heating gas and preventing new star formation. This is known as negative feedback in the context of galaxy evolution. However, in some cases, quasars can also have a positive feedback effect, triggering new star formation by compressing the gas in specific regions of the galaxy. This dual role, suppressing star formation in some areas while encouraging it in others, suggests that quasars, particularly double-lobed quasars, are instrumental in determining the ultimate fate of galaxies. The evolution of galaxies may depend heavily on the specific dynamics between the quasar and the materials surrounding it. As for the structure of the accretion disk itself, this is another area where double-lobed quasars continue to captivate astronomers. The accretion disk consists of hot, ionized gas that spirals toward the black hole. As the gas gets closer to the event horizon, it heats up dramatically due to friction and gravitational forces. The energy released in this process is emitted across the electromagnetic spectrum, from radio waves to X-rays. In the case of double-lobed quasars, the accretion disk's characteristics are vital for determining the jet structure. It is believed that the alignment of the accretion disk, especially relative to the spin of the black hole, plays a significant role in creating the jet's symmetry and directional properties. The hotter, denser material near the center of the disk is thought to be the source of the material that fuels the relativistic jets. This alignment of the accretion disk is also critical for understanding the orientation of the jets. Double-lobed quasars are believed to be powered by relativistic jets, which are emitted along the rotational axis of the black hole. The way in which the black hole's rotational axis is aligned relative to the observer's line of sight affects the appearance of the quasar. If the quasar is viewed at a higher angle, the jets might appear more aligned with the observer, potentially revealing the full extent of the double-lobed structure. Conversely, if the quasar is observed at a flatter angle, the jets may appear to be more confined, giving the quasar a different, sometimes harder to detect appearance. This variability in observation highlights how the orientation and distance of quasars can impact our ability to study them. One of the most captivating aspects of double-lobed quasars is their spectral diversity. By observing quasars across multiple wavelengths of light, astronomers can gain a much more detailed understanding of their composition, structure, and behavior. For instance, the radio emissions from the jets can reveal the presence of high-energy particles moving at relativistic speeds. At the same time, X-ray and ultraviolet emissions from the accretion disk provide insight into the temperature and density of the material surrounding the black hole. These multiple wavelengths work together to create a more holistic picture of how these quasars operate. Additionally, the interaction between the jets and surrounding intergalactic material can result in the emission of synchrotron radiation, which is especially prominent in the radio portion of the spectrum. The study of double-lobed quasars is also closely linked to our broader understanding of supermassive black holes. These objects, which typically reside at the centers of galaxies, are thought to be key players in the formation and evolution of their host galaxies. As quasars are powered by supermassive black holes, the study of double-lobed quasars provides crucial information about how black holes influence their environment. For example, the energy feedback from quasars can regulate the accretion rate of material onto the black hole, affecting its growth. Moreover, by observing the evolution of quasars over time, scientists can gather data on how black holes grow and how their influence propagates outward, affecting everything from star formation to the intergalactic medium. To fully understand the dynamics of these massive systems, it's essential to look at the interactions between black holes, quasars, and galaxies from a multidisciplinary perspective. This means considering the roles of dark matter, dark energy, and the large-scale structure of the universe. Dark matter, which makes up a significant portion of the universe's mass, could be a critical factor in determining the formation and behavior of quasars. Additionally, the interplay between dark energy, the force driving the accelerated expansion of the universe, and the massive energy output of quasars may offer insights into the large-scale evolution of the cosmos. The study of double-lobed quasars offers not just a glimpse into some of the most extreme and energetic objects in the universe, but also provides valuable insights into cosmic evolution, black hole dynamics, and galaxy formation. Through their immense energy output, powerful jets, and unique interactions with their surroundings, these quasars are a critical component in understanding the universe's fundamental processes. As we continue to explore and study these objects, our understanding of the cosmos will expand, shedding light on everything from the nature of dark matter to the formation of galaxies themselves. Double-lobed quasars, despite being some of the most extreme objects in the universe, hold within them the potential to revolutionize our understanding of the universe's formation and the interplay of fundamental forces. They are more than just cosmic phenomena. They serve as natural laboratories for testing theories about the laws of physics under conditions of intense gravity, pressure, and energy. By examining these objects, scientists are able to probe the very fabric of space-time, testing predictions made by Einstein's theory of general relativity in environments where gravity is at its most extreme. The study of double-lobed quasars also plays a critical role in our understanding of cosmic evolution. In the early universe, when galaxies were first forming, it's believed that quasars were far more prevalent than they are today. The energy produced by these objects, as well as their feedback effects on surrounding gas and star formation, likely played a significant role in shaping the early universe. The powerful jets emanating from the black holes at the centers of these quasars would have impacted the surrounding environment, potentially contributing to the reionization of the universe. This period, which occurred about 13 billion years ago, marked the time when the first stars and galaxies formed and began to illuminate the universe, gradually ionizing the hydrogen gas that filled space. Understanding double-lobed quasars and their jets is crucial to unraveling the mystery of galactic evolution. As previously mentioned, the energy and material expelled from these quasars play a central role in either quenching or stimulating star formation in the host galaxy. The concept of feedback is vital here, where the energy produced by the black hole prevents the galaxy from becoming overly efficient at forming new stars, thus regulating the galaxy's growth. This concept is not only applicable to individual galaxies, but also to large-scale cosmic structures. By analyzing the feedback mechanisms of double-lobed quasars, scientists can understand how galaxies interact with their surroundings and how their evolution might be governed by their central black hole's activity. Moreover, double-lobed quasars serve as natural beacons in the study of cosmic distances. Because they are so bright and luminous, quasars are often used as standard candles for measuring distances across the universe. The light emitted from these objects travels across vast expanses of space, offering a snapshot of the universe's past. This is particularly useful in understanding the expansion of the universe. By comparing the redshift of the light from distant quasars to their distance from Earth, astronomers can make important measurements about the rate at which the universe is expanding. This is fundamental to our understanding of dark energy, the mysterious force that is driving the accelerated expansion of the universe. In addition to their role in cosmic measurement, double-lobed quasars are also a powerful tool for studying relativistic jets. These jets are created by the extreme conditions surrounding the supermassive black hole at the heart of the quasar. The material spiraling toward the black hole forms a highly energetic disk of gas, which is often accelerated to nearly the speed of light by powerful magnetic fields. These jets can stretch for millions of light years and are often visible in multiple wavelengths, including radio, optical, and X-ray. This allows scientists to study the jets from different perspectives and understand the physical processes occurring within them, such as the acceleration mechanisms and the structure of the magnetic fields at play. The study of these jets also contributes to our understanding of high-energy astrophysics. As the jets from double-lobed quasars move through the surrounding intergalactic medium, they interact with the gas and dust in their path. These interactions can generate a range of high-energy phenomena, such as the creation of shock waves and the emission of high-energy particles, including cosmic rays. The energy carried by these jets is immense, and the ability to observe these high-energy processes across vast distances gives astronomers a unique opportunity to study the fundamental physics of particle acceleration, magnetic field generation, and energy dissipation on a cosmic scale. Despite their importance, double-lobed quasars remain somewhat enigmatic. There is still much to learn about how their jets are structured and how they interact with the environment surrounding them. For example, the detailed nature of the interaction between the relativistic jets and the gas in the host galaxy is not yet fully understood. Some models suggest that the jets can shock the gas and compress it, triggering star formation in certain regions of the galaxy, while others propose that the jets can heat the gas and prevent star formation entirely. The exact nature of these processes likely depends on a variety of factors, including the size and orientation of the black hole, the rate of accretion, and the composition of the surrounding gas. One of the most exciting aspects of studying double-lobed quasars is the potential to observe them in real time. Quasars, due to their extreme luminosity, can be seen across vast distances, often as they appeared billions of years ago. However, thanks to modern instruments, such as radio telescopes and space observatories, scientists are now able to observe quasars in real time and track their evolution. This real-time monitoring allows for the detailed study of the dynamics of the quasar and its jets. For instance, recent observations have shown that some quasars exhibit variability in their brightness on short time scales, suggesting that the processes at work in the accretion disk and the jets are highly dynamic and can change rapidly over time. This variability adds another layer of complexity to the study of quasars and further challenges astronomers to refine their models of these fascinating objects. In addition to their role in understanding black holes and galaxy evolution, double-lobed quasars also provide crucial information about cosmic magnetism. The jets emitted by quasars are highly magnetized, and their study provides insight into the behavior of magnetic fields in the extreme environments near black holes. The strength and structure of these magnetic fields play a key role in the formation and acceleration of the jets, and by studying the way the jets interact with these fields, scientists can gain a better understanding of how magnetic fields behave in other extreme environments, such as in pulsars, magnetars, and neutron stars. This research has broader implications for our understanding of magnetism on cosmic scales and how it influences the evolution of astrophysical objects. The study of double-lobed quasars contributes to the broader field of cosmology by offering a detailed view of the large-scale structure of the universe. The interaction between quasars and their surrounding galaxies can affect the distribution of galaxies and clusters of galaxies, providing insight into how the universe has evolved over time. The energy output from quasars can also impact the intergalactic medium, shaping the distribution of gas and matter throughout the universe. Understanding these processes is essential for building a comprehensive picture of how the universe has evolved from its early days to its present state, and how it will continue to evolve in the future. Double-lobed quasars are among the most fascinating and complex objects in the universe. They are not just a tool for studying black holes and galaxies. They offer insight into the fundamental forces that govern the universe and provide a unique window into the extreme environments where the laws of physics are pushed to their limits. As technology advances and our ability to observe these objects improves, we can expect to uncover even more mysteries about the role of quasars in cosmic evolution. The study of double-lobed quasars will continue to be an essential part of our quest to understand the nature of the universe, from the smallest scales of particles to the largest scales of galactic clusters. This video is for educational or entertainment purposes only, and information provided in the video may be incorrect. Like the video and subscribe to the channel for more such amazing videos.